public. Preparing live stream. It's about halfway through the progress bar. Looks like it's popping in, and we're live. I'm on mute. Less than 1 minute ago. Hey, so we're going live. We're on YouTube. Let me give you the link, and we're going to put that in Facebook. In the chat here, that's the YouTube link for live. Okay, and I'm going to, with YouTube Live, there's about a 35-second delay. With Facebook, there was like a 2-second delay of that, just so you know. Let's see, Facebook. There was like a 2-second delay of that, just so you know. Let's see, where'd that come from? Mute, mute. Why am I getting a, where's that audio coming from? Good morning, everybody. We're working through some technical difficulties. We're switching over, and you're probably seeing us on YouTube, maybe randomly, but I am going to update our to get the stream running this morning on Facebook. Cool. All right. And what's funny is I'm pushing YouTube through Facebook. So good morning, everybody. I think that works. We'll see what happens. There's some technical difficulties this morning connecting to Facebook Live. Little spinning wheel for 20 minutes. We've tried 4 or 5 times to connect. We're not, so we're on YouTube Live. The link should be in right there underneath or just above the video. If you're on Facebook, pointing you to YouTube. Tony, I don't know if you can direct any traffic to YouTube outside of Facebook, but we didn't run any kind of promotions or any drivers to this. We might want to set that up if we're going to have to go this route again. So yesterday, we were really fortunate to have Dr. Richard Barker join us from the Gilroy Lab and talk about an inspiration. 3 solid packed hours of a wild ride through microbiology, through plant biology, through data science and visualization, through interesting behaviors of not just plants, but animals. The research they're doing at the lab is the personal things that he's working on. The curious mind took us on an amazing path that is down below on our Facebook feed there at Magnitude.io. You will see the recording. So if you haven't watched it yet, it's definitely, get yourself a nice cup of coffee or hot cocoa and tea, sit down and enjoy the musings and as Dr. Parker does a deep dive into the possibility. And it sounds like he might even join us today. So if he pops in, we'll have a chance to explore a little bit further. What I want to do, and hopefully we've got the folks that are popping in and checking it out, is go a little bit more through Exolab and what that actually is. So the primary objective of Exolab, this is an Exolab unit behind us. We really didn't, that's kind of the star of the show here with respect to the Leguminaut challenge. So let's walk through the anatomy of what an Exolab is. And Tony, if you can check with me, I think we are live on Facebook now, or should be.
Yeah. Oh, hold on.
Yeah. With a bit of a delay. So this is the Exolab. Think about it as a intermodal transportation for space. So instead of a 40-foot container on the highway on a 18-wheeler or on a series of train cars or on a ship that goes across the ocean, The intermodal transportation for space is a 10 centimeter cube. And actually, I think I have one around here somewhere. I'm going to go try to dig up. But if we can get something in that 10 centimeter cube that weighs no more than 1.33 kilograms, we basically have something we can put in space. Now, that could be a satellite. And you think about these as building blocks. So someone might make a 1U equivalent or 10 centimeter cube at 1.33 kilograms. Or they might actually make something larger like a 2U, putting those together, or a 3U. Hey, Steve. So we actually bumped over to YouTube Live because Facebook just was not connecting. But it looks like we are live in YouTube. And the funny thing is I bumped back around to Facebook. So we're watching YouTube Live through Facebook. Okay. The delay is about 30-ish seconds. I'll be on YouTube. But what we're doing here is we're kind of rebooting from yesterday. Dr. Parker took us on such an amazing deep dive into the realm of possibilities that we're pulling back a little bit. Going to talk about the star of the show, Exolab, walk through some of its functions and features, and then get into kind of the Leguminaut challenge specifically. Okay. So, please feel free to kind of join in with me and share what you know. So, and Tony's with us here. Tony So is our co-founder, and I guess I should introduce myself. I'm Ted Tagami, co-founder of Magnitude.io. And we've been doing some crazy stuff over the last 7 years, bringing learning right to the very edge of discovery the best we can. So I was talking about intermodal transportation and this idea of the 10 centimeter cube. Essentially, if you can think about that like you would a 40-foot container on the back of a truck or on a ship or on a train. If you can fill that little package up, it's much easier to get to space. There are providers that can hook us up, and just like if you're at a port, in this case, go on a rocket, like maybe a SpaceX rocket or a Northrop Grumman rocket, resupply mission to take us up there. And once we get up there, I'm going to have to dig up a little video here, but the astronauts take us out of a flight bag. We might have been in cold stow, or we might have been stored in ambient conditions, depending on the experiment. We then get loaded onto a data card. So imagine this is an aluminum box rather than this beautiful little device we'll get into in a second. This is what we normally see in the museums, in the science centers, and in the classrooms. But imagine this is a 20 centimeter long by 10 by 10 centimeter aluminum box with some fans on it and a adapter port with data and power. So they take this aluminum box that we've sent up in that flight bag, and either like a SpaceX Dragon or a Northrop Grumman Cygnus, and they attach it to that data card, and then they slide that data card into a locker. And that locker has a number of cards in it. I think right now the current configuration, there's 3 cards in the slot with a half bay left over. And then they close the cover, and the instrumentation, there is the front for the astronaut to essentially boot up the device to ensure that our lab is now operational, functioning, that imaging is occurring and data is coming down to, I believe it goes to Houston first, and then it gets piped out to our ground crew. Big shout out to Space Tango in Kentucky. Without them, we would not be in space. And Twyman Clements there, the CEO of Tango, is an amazing gentleman. His team is absolutely phenomenal, and they really will work with you if you're doing more advanced research and you're looking at doing things in space. It does get quite expensive. And our approach was to take the single device, get it up to station, and then spread that cost out across as many schools as we could. In this case, this current experiment has about 130 teachers in it, anywhere from Africa to Europe to here in North America. Mostly it's domestic. We have most of our experiments running here. Now, what we will talk about is that during this pandemic, when we're mostly forced to shelter in place, or being asked very politely, and I think we'll probably have to enforce that a little more firmly, to shelter in place. Many schools have closed down. We're not asking you to actually have to go and use this device to get the full experience, to get the full fidelity of what we're doing. We're instead going to be turning around to a design challenge in which the experiment that we're running that's coming up here in August, you guys get to help us select what we're going to put in this Exolab. So let's talk a little bit more about it. We know that we send an aluminum box up to space, and what's the difference between what's up there and what's on the ground? Well, there are some extra sensors that are on there. We have some redundant temperature sensors, for example. I think we have other gas sensors that aren't in the ExoLab. We wanted to keep the cost at a minimal amount. But let's look at the ExoLab in the classrooms themselves and show you what an experiment might look like. So there is a nice clear acrylic cover, and you can see there is a nice little scale here in centimeters for students to look at and observe perhaps the change in growth over time. You know, watching a plant grow is kind of like watching paint dry, and especially for our younger students, it's not too exciting. But in typical fashion, how it's used in the classroom is students might come into the class and make an observation that morning or at the end of class or once a week or what have you. In the libraries, it's when they drop off their books and pick up other books. It's like a bug light. They head over to the experiment. They see books that have been curated by the librarian, and they look and see what the plant has done. In those library situations, we usually have something like the ISS Above, which is a live view of Earth with some really cool telemetry by ISS Above. And it's a really great little device to hook up and kind of get a, well, first of all, a live view of Earth, which is pretty awesome, but also other information about what's happening on station and just in general, what's happening in a big way with NASA as an organization. And I think other cool space stuff as well. But the lab itself, I'm going to take out the experiment that's currently running. We'll look at that in a second. But this is that 20 centimeter cube by 10 by 10 that we have in the classroom. We've got an LED array here, 8 by 8, that that has an adjustable wavelength of light, duration, and intensity. Now, it's been preset for the current flight missions, but it always can be adjusted if someone wants to do a separate experiment, or they're very curious about what might happen in a different wavelength of light, lower intensity of light, or even longer or shorter duration. So all that's kind of adjustable. And these are all conventional off-the-shelf components. Again, cost being a consideration, we wanted to make sure that I'm going to get something here I can point out some objects. Wanted to make sure that many schools could use this device. There's something here. I'll use this. Yes. So this big gold box here on the top is a carbon dioxide sensor. So we're getting ambient conditions in the environment here. So this would be in my garage at home where I'm getting the current CO2 levels when it's plugged in. It might be in your classroom or what have you. So it is ambient. We're not controlling that. Probably wouldn't want to pump a bunch of CO2 in a classroom anyway. This little pinhole just above this green bar that's popping out is a hole for temperature and relative humidity. So we're getting a sense of how much moisture is in the air and what that temperature is in Celsius. And that bar that is sticking out, that little PCB has it might be hard to see, especially with my lighting down here, but is a light sensor to kind of keep track of how much light measured in micromoles per square meter, I believe, is coming from our light to kind of when we get our visualization. If Tony's with us here, he can share our dashboard a little bit more detail. And so with the CO2 sensor, the temperature and humidity and light sensor, we also have a wide angle camera. Now this camera takes an image once an hour. And what's cool about a plant growing is it does throughout the day follow the sun. And if we have it out in the open here, you can see that. And it's going through its growth. If you just look at a plant, you don't think it's doing much of anything, but your house plant, your plants at the office and plants out in the field and yard, they're moving just like we are. They're just got a little different pace, a little different rhythm. And it takes a little while to actually see that. And so that time lapse, in essence, that image that we capture once an hour gives us an indication of what's happening with the plant. And so those are the instruments that we have on here. And for the engineering curious out there, this is running on a Raspberry Pi backplane, and it's connected via Wi-Fi to a local network. Data coming from this device, the temp, humidity, CO2, light, and the imaging gets sent up to the cloud, our little Magnitude cloud. It's gathering data from all the instruments around the world, the instruments that are aboard the space station, and getting that down as well. And we have a beautiful visualization dashboard where we can see what's happening with this plant in this environmental condition and this one with that condition. And of course, in microgravity, what that plant might be doing in response to the lack of it. Very little effective gravity up there, and so the roots are behaving slightly differently. The, the, the rest of the plant's development changes. And there are other changes that can occur. We have some temperature and CO2 anomalies, and they're different than what we see here on Earth, so that can affect our plant. So this is our device. Oh, and for the engineering minded, one extra step, this little light sensor is an I²C port, and we can just pop that right off, 4 pins. We, in theory, could daisy chain this port and add additional sensors. And so brilliant young engineer, Kareem Sheikh, kind of took our vision and manifested it. And I think this might be the 3rd or 4th generation of Exolab. We have a nice big open bay in the back here in which we could perhaps in the future add infrared, ultraviolet, spectroscopy, microscopy. There are a lot of restrictions, physical restrictions on depth of field and other things like that, power requirements. So that's definitely an engineering investigation if one's so inclined. Now we're sticking with this form factor because it mimics what we have in orbit. That's not to say we can't do something like imitate the veggie. The veggie on a space station, it might be what, a half a cubic meter volume. It's probably a little larger, and it's out in the open cabin there in the on the space station, and they're growing their plants in a different system. In fact, Tupperware has a system they're testing now called Ponds. I'll have to look up that acronym again, but it's a way for the astronauts not to have to tend to those plants so frequently. We use an agar medium, which I'll get to our actual experiment in a second here. But if we want to look at the full life development of the plant, not just early germination and root development, then we'd probably go to something more akin to the veggie. There's also another, and there's probably several other instruments up there right now, the different researchers that are doing the typical plate that you'll see up there in these kind of investigations. But there's another device that they're called the Advanced Plant Habitat, APH. And I understand there's more than 100 sensors inside that device, and it is controllable. So you can adjust to the temperature and humidity and what have you. A lot of really cool things. I imagine that queue, starting with your advanced research, is probably pretty deep. Our dream is to actually maybe get inside that APH and do some stuff with a higher fidelity. So this is our device, the Exolab here on Earth. Imagine a big aluminum box, the same volume in space, and slapped onto a data card. It slides into a locker. It gets powered up for usually about anywhere from 25 to 35 days. We had one mission that was up. We got a ride on one flight and we got a ride home on another. So we rode up on a Northrop Grumman mission and came home on a SpaceX Dragon, kind of like what we're doing on this current mission. Mission 7 just got bagged up and it's coming home on April 10th, I believe. It was originally scheduled for April 2nd. The Dragon's going to take us home. We went up on the Grumman, NG-13. So our experiment. So we changed experiments up each flight, and some folks like Dr. Barker have recommended that we keep a continuity. So we're going to be exploring what we can do to maintain continuity in these experiments and get a higher fidelity of data and information with each subsequent mission. This helps researchers, unlike our just curious investigations, to actually build a corpus, a body of work that can then be used to prove a hypothesis they might be generating. And so we hope that we can work with Dr. Barker at Gilroy and other scientists based on what their needs are. So instead of us kind of tail wagging the dog here, thinking about K through 12 or K through 16 undergraduate learning, that we're really kind of moving more to the advanced research and then backing back into what we can do for students to engage them in the exciting world of the International Space Station and things like plant biology and even bacteriology. So our experiment. So Flight 7, the mission that we're flying on right now, we're flying these cowpeas or black-eyed peas. Vigna is the Latin. Growing these with a bacterium because they actually form a relationship if everything goes right. bacteria is Rhizobia, and Rhizobia takes nitrogen and basically fixes it and has it available. Could be pathogenic apparently, but what it becomes symbiotic when it comes across a legume like the cowpeas that we have. And I'll just take one of these out of the holder. So this is a 38 millimeter by 238 millimeter diameter, 200 millimeter tube. And here's our nice little plant here. This plant was planted on February 28th. So it's getting to be 3 weeks or so old. You can see some little black specks there. That's an inoculum. That's the rhizobia as a powder. We go through a process in which we, with the students, sterilize the seeds, have them germinate, following a protocol, and then we plant these in this agar. This gel, it is a gel, it's not a water, because in space, water acts and behaves really quite differently. We wanted something that kind of glom together. It's mostly water, 98 something percent water. Your seaweed kind of acts as a binder. And then we add nutrients into the medium as well. Now I might mess the name up a little bit here, but it's Muroshige and Skoog, I believe, is a pretty conventional medium of salts that are the nutrients for most plants. And that's formulation you can go to source like Carolina Biological. In fact, we get our agar through Carolina for most of our biological needs. For our plants, our seed sources, we go to the best source we can find, whether it's heirloom or hopefully research grade seeds. So this is the inoculum in this one. And the other plant is the same plant, cowpea, vigna, and it's been sterilized and prepped the same way, but it does not have the inoculum, okay? And so I didn't really get into the relationship between this bacterium and the legumes, but they've got an interesting little barter system going on. The plant is, through its photosynthesis, is creating some extra carbon. And this bacteria, I think, really knows what's going on. I don't know if it's smelling it or there's some kind of chemical reaction, but it looks for these legumes, and it begins this dance around the root structure, and it's going through its process of just fixing nitrogen anyway. And so what happens at the roots, these nodules develop if everything works properly, and there's an exchange of these gases, of a carbon and nitrogen. The plant, and Dr. Barker, I wish you were on here. If you pop in a little later, we'd give us some more detail. But this is where nitrates and nitrites and ammonia and other things kind of happen chemically for the plant to really flourish and fully develop. Without this symbiotic relationship between rhizobia and legumes, we wouldn't have things like alfalfa or a clover or maybe some of your favorite beans, like a black-eyed pea or red bean or what have you. And so this is an experiment we've just completing right now, looking at this interrelationship and what might happen when we've ripped out this force of nature. That evolution here on Earth is pretty much gone as long as we've had life on Earth, factored with this gravity vector. It's gone now. Very, very, very little. It's still there, but it's very little. Pulling back from that, why is there very little gravity? Well, here's that view of Earth behind me. That's a live view from the International Space Station. And if you look at an astronaut on the space station, they're floating around, right? It's not because there isn't any gravity. So here's the freaky thing. They're falling. They're falling all the time. So you might have been on a roller coaster. You get up to the top and you drop. Your stomach literally is floating in microgravity for a moment. You can feel it. You're in an elevator maybe, and that elevator drops suddenly. That feeling you get, you literally you have a 0G experience, only just for a moment. These astronauts are in a constant state of falling. And how is that, and why does it work? Well, if we look at what an orbit is falling, but you keep on missing the body that you're going around. And so you have to travel at a pretty high rate of speed. Imagine just a flat Earth here. We launch something up like a rocket. It's going to have a parabolic arc. It's going to come up. If it doesn't have enough force, it's going to come back down again. we've had one of our missions. We do a lot of cool stuff with high-powered rockets and high-altitude balloons. We had one rocket we launched. We didn't launch, but we got a ride on out of White Sands, New Mexico. It went up about 60 miles, pretty much to the edge of space. That's really high. And it turned around and it came right back down again, because it's not how high you go that gets you out of Earth's atmosphere. You actually have to be going fast enough around the planet. So as you fall, you keep on missing the planet. If you can imagine that, here's Earth. We're moving so fast as we're falling. Whoops, the flat Earth is not flat, it's round, and it's going so fast that we keep on missing it. So the International Space Station is about 250 miles up above the surface of the Earth as an average. It's at an inclined plane, slightly tilted to the axis of our planet Earth. And so if you look at, you might see some diagrams in the back here in a moment, it looks like a sine wave as it travels across the planet, and it kind of moves to different regions of the world as it moves across this, what looks like a sine wave on a flat diagram. But it's traveling so fast that it keeps on missing. How fast does it go? It's going about 17,500 miles per hour. That's going really fast. So that's how they're getting the microgravity. They're falling. Wow. And so you got to get out a lot farther. And I don't think you can ever escape gravity. I mean, our sun is being yanked around the galaxy by the black hole in the center. And our galaxy is being influenced by other galaxies in the universe. And all that gets far beyond my pay grade as far as trying to figure out how all that works. But I don't think you can really go anywhere in the universe and have no gravity. And please, if there is a physicist out there or someone that really understands these concepts much greater than me, please weigh in on this. Help me understand, could there be anywhere in the universe in which there actually is an absence of gravity? And I don't think that's possible. But anyway, so we're looking to see how our planets might behave in this microgravity environment as this International Space Station is flying around the Earth. Every 92 minutes, it's going a complete orbit. These astronauts are getting more than a dozen sunrises and sunsets every day. So I can't imagine trying to sleep in that cycle. But there you have it. So what we're doing here in our Leguminaut challenge is this legume we flew, the cowpea, but we're curious if we can get maybe a different plant to grow more successfully. We didn't really see nodulation for a couple different reasons on Space Station. And so we're opening this up to looking at and investigating many other different types of legumes. And again, I mentioned already clover and alfalfa, they're part of the legume family. Your beans, whether they might be like red beans or chickpea or whatnot, peanuts. So all of these potential candidates are up for a nomination, right? And your job as educators, if you're students at home and you're dialing in and checking us out here, dialing in, that's an old term. I guess no one really dials in anymore. But if you're logged on and you're here at YouTube or Facebook and you're seeing this, your challenge is to look at all these different legumes and try to determine which one would be the best candidate. Now we have a broad selection of learners that are joining us in this mission. And I hope that we can do that advanced research in which someone might say, well, I'm very interested in this root structure development, or we notice that there is a certain expression in these genes and we want to see what these genes can do. And this plan has been used in research. So I encourage our really adventuresome students to dig in, and our teachers that are maybe in honors AP or AP biology to at the high school level. Hey, if you're in advanced middle school, jump in. Primary school, and you can really handle this, dive on in. What can we learn about microgravity from these different candidates that we'd like to fly? Maybe you actually you're very passionate about a legume that we haven't listed. Recommend it and give us an argument why. What we're doing is we're developing teams across these different legumes, and we want you to find and get your support behind it and provide your arguments why. Now, here's where it gets fun, because we have younger students and we might have teachers that just want to engage their students while they're staying at home here during this really quite remarkable time that we're all living in, and just have a creative approach to this. Our younger students, they might just get out a nice big sheet of paper and some pens or some crayons and draw some pictures of what it's like on the space station, or what plants do, or what their favorite meal might be based on legumes. So please, feel free to be creative about your argument why you want to select a particular legume over another. And Tony, I don't know if you can do this, but if you're on right now, if you haven't stepped away, if we can pop up the Magnitude.io page so we can show some of our candidates, I think that'd be really good. And we can look at what some of these candidates might be capable of doing. But yeah, so you can do an interpretive dance. I heard someone say that, and it's kind of stuck in my mind, like, I'm growing in microgravity and I'm a legume. So you can do something like that. You can write a poem. You can do other investigations. This medium that we're using, maybe although we're doing a legume challenge, you're kind of fascinated, but what is agar? What's that all about? You might want to go out and just go to the grocery store, or next time you go out to get your supplies and your toilet paper. Everyone's got more than enough now, right now, I hope. And go out and get some gelatin and make your own little kind of agar. Put some, maybe put a little seed in it and see what can happen. You're going to want to germinate your seed first. This one might be a little on the thick side. So our plants have to work a little hard to get those roots down in there. So maybe a little diluted. So getting that right concentration could be important. Tony, thank you for sharing that. So what we're looking at right here, these are our candidates. We would like to fly all of these little guys, but we want your feedback on which one would be the best. So again, scientific research, give us a supporting argument why we think red or white clover or mung bean, lentil would be the best candidate to fly. Or if you really just want to be creative about it, write a story, draw a picture, find a reason why one wants to be excited. Be the kind of the PR for alfalfa, right? Or the representative of soybean, right? And a lot of these, of course, you probably recognize, like how often soy is used. All of the legumes are kind of also considered as green fertilizer because of those rhizobia. It's not the legume per se, but it's the rhizobia that's making that fertilizer category become a reality. Because that, if you recall, the rhizobia is fixing that nitrogen, and that is more than the plants can actually use. And when the plants go through their full life cycle, they either get harvested or they get turned back into the soil. But those nodules that were developed there become nitrogen in the soil for the next plants that you decide to grow. So Native Americans, I think, really understood this well. And it's called Three Sisters. And they took beans, squash, corn, and they kind of grew them together. And that interaction of nutrients allows you to perpetuate a really kind of organic and non-chemical process to engage healthy kind of growth. And if you're planning on some spring gardening, maybe you might want to try that yourself. Planting some beans along with your corn and squash and seeing how they do season after season. I think you'll be happy with the results. So which candidate do we want to fly? And I'm not sure I can speak much to these. If I have any of the team leads on, and let's see, Steve, I think you're on. You've got lentil. You want to share anything about our lentil candidate?
Oh, lentils are fantastic. You can do all sorts of things with lentils. And I found out that apparently, and I'm surprised Diana Phillips didn't take this one. It's the #1 producer in the world is Canada for lentils.
Okay.
So I'm kind of surprised she didn't take that. But yeah, I found all sorts of neat things about lentils, but I'm excited to see what the students can find out. So I don't want to show my hand too soon.
Oh, okay.
I want to see what they could find.
All right. So is it just Team Lentil, or do you have a?
I'm calling it Team Lentil right now. I'm really hoping that there can be somebody that jumps on board that can give me a better name than that.
All right, let's get it together for Team Lentil. Hands up. Yeah, go Team Lentil. Now, one of our interns, C, she's a researcher here. She actually graduated from UC Berkeley in planetary science. you have questions about planets and exoplanets and what have you, talk to C. She's pretty awesome. But she's actually categorizing these things, and we're giving them some stats. So if you look at 100 grams of cowpea or 100 grams of garden peas or adzuki, what are its characteristics? How many grams of that 100 grams is protein? How many grams of that is carbohydrates or those other nutrients, right? Your vitamins, what percentage of your daily requirement does this particular legume offer you? Because as we grow these things in microgravity, we're kind of thinking about, oh, there we go. Thank you, Tony. Why are we going to use this in space, right? And so, wow, we want to go to Mars. We want to, build a settlement on another planet. That's several decades away. If we want to expect to have something persist beyond just kind of putting a flag there and saying we've done it like we did in the 60s and 70s on the moon, then we're going to need to find a way to perpetuate an agricultural system. And they want to do this on the surface of the moon as well. But let's bear in mind and take a big step back. Your lunar surface and your Martian surface, it's basically dust, rock, crushed rock, nothing organic as far as we can find. Now there's water ice, and there's hope that in that water ice we might find some forms of life perhaps, but there's pretty extreme environments. To give us any indication, when we launch our high altitude balloons here on Earth, we'll send them up with our students, 19 or 20 miles. Gets up into the stratosphere. You actually get up above the ozone layer. And the density of the atmosphere here on Earth, I consider it like 100% dense here. By the time you get up to 19 or 20 miles, it's about 1% of that density that we have down on Earth. Something like a barometer can measure barometric pressure. And that pressure changes as you rise in altitude, thanks to gravity. And a great way to visualize this, I love this. If you've ever done a dog pile during the summer, you and your buddies jump on top of the unwitting suspect, that person at the bottom is feeling crushed. And of course, if you're on top of that dog pile, you feel pretty liberated because there's nothing above you and everything's below you. Well, instead of you and your friends being in that dog pile, imagine that you are molecules, your nitrogen and oxygen molecules, your argon, the gases in the atmosphere. It's mostly nitrogen and oxygen, like think 75-25, close enough. There's a balloon flight there, one of our launches. And so those molecules here at the surface of Earth are getting crushed by all those other molecules going all the way up. As I mentioned, about 62 miles up, they call that the Kármán line. It's an arbitrary line. They pretty much say that's where space begins. It's hard to tell. I mean, there's little oxygen molecules, I'm sure, floating around by the space station all by themselves, lonely, looking for somebody else. Obviously, the helium and the hydrogen are kind of finding their way off. They're lighter than the other gases, so they're getting all the way up there. And so we have a more dense atmosphere here on Earth. And as you go up, a much lower density. And when we get up around this 20 miles, like what we're seeing here in one of these flights, I'm not which, this was out of Stockton, California, in the Central Valley. And this was done, I guess, last year and back in about a year ago. That is actually the Sierra Nevadas, and you can see we had a good snow that year. I don't think we had that kind of snowpack this year. As it spins around, we're probably going to see the California coast, Monterey, San Francisco Bay Area. Mount Diablo is a big mountain, and they actually use it as a geo-reference for land surveying. So all the plots of land that are out there to make sure all the streets are all lined up and whatnot, they use these coordinates like Mount Diablo, and you'll probably see that in here. But I digress. Up there at that altitude, at 19 or 20 miles up, it's about 1% of what we have here on the surface of Earth. Well, on Mars, the atmospheric pressure is about the same on the surface as it is 20 miles up. And another interesting fact, it's really, really cold up there, -40, -50 degrees Celsius there in the stratosphere above the ozone layer. And the surface of Mars, it ain't much warmer. So if you want to experiment, now the composition of the gases is quite different. Instead of nitrogen, primarily nitrogen and oxygen, we've got primarily carbon dioxide on Mars. So you're going to try to grow some plants in a very thin atmosphere with primarily carbon dioxide. Oh, wait, what do plants like to eat? Oh man, they just give me carbon dioxide, right? And they're really, if you talk about symbiotic relationships, right? We're exhaling carbon dioxide and they're breathing it in. And what do the plants exhale? Oxygen. Whoa, speaking of which, what just happened right there? Our barometric pressure, our helium balloon continue to expand because of lack of pressure, filling up the emptiness around it until, I don't know if you've ever blown a bubble gum before, but it gets to the point where it just bursts in your face. In this case, that balloon got so big that it couldn't do it anymore and it basically burst. We're now kind of on a free fall. Our parachute just kind of waving around right now. There's not enough atmosphere for it to really get filled up. Eventually it will fill up and descend nice and slow. But this atmospheric effect up there, very thin atmosphere, very cold, is what Mars is like, mostly carbon dioxide. But again, back to the regolith. Where's the soil? Where are the little bacteria? Where are the little bugs? The worms, the nematodes? Where's all those little creatures that turn the soil and the bacterium that help kind of create the dynamics that through evolution, through millions of years, have created these alluvial soils that can actually harvest and grow life. If you look at the Indus Valley region or the Central Valley here in California, or other great growing regions, those were originally part of, they were part of the ocean and riverbeds and streams. And this was accumulated over time, plant growth and animals. And this rich nutrient soil, it's not rock, right? We don't have that on Mars. We don't have that on the surface of the moon. How are we going to grow any kind of settlement beyond Earth? We can't continuously lug our stuff out there. You ever gone on a backpacking trip? You can only fit so much on your backpack before you can't carry it anymore. What's nice about a backpacking trip, though, as the more you get tired, the less you're carrying, which is kind of nice. But you got to make sure that your journey, by the time you get back to the car, is that you had enough food and water. So you got to plan appropriately. Now, talk about a long backpacking trip, 250,000 miles to get to the moon, and whoa, 6 month travel to get to Mars. Well, you better make sure you got enough food with you. And that's a lot. Now let's talk about rockets. A very efficient rocket, 95% of the mass of that rocket is propellant. Because remember, we got to get going really, really fast, 17,500 miles an hour. We got to punch through the atmosphere and get into, at least into orbit. But if we want to leave orbit, we got to go even faster than that, right? And so we go less than 17,500, we're falling back to Earth eventually. Faster than that, we're going to be leaving our orbit. Will get larger and larger and larger until you actually get to a point where there's enough of your speed, you're going to leave. Now, what's your trajectory? Well, hopefully you've done some math and you're on the way to the moon, and you're going to work your way there and circle the moon and maybe go into something in the near future called the Deep Space Gateway, which is the future version of what we've learned for 20 years aboard the International Space Station. How can people live in microgravity? So they've just started to announce the new companies that will be building the gateway, which will be in lunar orbit, be a way station for astronauts to go down to the surface of the moon for reconnaissance missions, to look for that water ice, to think about where it would be nice to place a habitat. Again, let's talk about the food. Where's it going to come from? At Magnitude, we're really, really curious about it. We think about our 6th grade students that are in school today, 12 years old, or high school students, 15, 17. In 20 years' time, we might have someone put their boots on the surface of Mars. Well, the average age of an astronaut that gets recruited into the NASA program is 34. So if you are 14 today, your students are 14, in 20 years' time, they will be an astronaut recruiting age. That's the Martian generation. So your students that you're working with, and students, if you're watching, I was a little kid. I was 6 years old when I watched them go to the moon. It's super exciting. You're the Martian generation. You're older than I am. I was then. And you're learning about cool things now. And information has become much more accessible. You've got the entire world's knowledge in your phone, right? It's what question do you want to ask? And with Exolab and with Magnitude and our experiments on the space station with our plants, in this case, legumes, we're trying to find the right candidate to begin this exploration, because legumes provide a great source of protein, good source of carbohydrates, nutrients, they're nutrient dense. Which one is the right candidate? Which one maybe doesn't consume as much resource. Maybe it doesn't need as much water. Maybe it grows really fast. Maybe it grows slow, but it's very dense in nutrients. So there are a lot of different characteristics. We're not quite sure how any of the, and maybe some of these may have never even flown to space before. Your argument might be, you know, I want to give this plant a chance because it looks like it's pretty good here on Earth. And so what it's going to do in space. So all these ideas are open. There are no rules other than we're going to stick to legumes, and we have to decide in the next 34 days. We started this yesterday, the first day of spring. So welcome to spring. Kind of got equinox, right? Where the sun is in our planet, northern hemisphere and the southern hemisphere are about equal in day and night. Now our days are going to get longer because of how we're oriented to the sun here in the northern hemisphere. And in the southern hemisphere, we're going to be a little further from the sun as it's tilted away, and our days are going to start getting a little shorter as it moves around the Earth. And so as we get to summer here in the northern hemisphere, winter in the south, our days are going to get really long until late June 20 something. We'll have the longest day of the year. And so right now we're just getting into springtime where everything's kind of even. And we're going to run this contest until an arbitrary date called Earth Day. I don't think there's anything about the heavens that gives us Earth Day other than we thought that was a cool day to celebrate our planet, April 22nd. So that was our time frame, because we've got to get our experiment to NASA, and they have to say, well, there's no toxicology issues here. These plants are good. You're keeping it well sealed, so astronauts don't have to breathe that rhizobia, and the rhizobia is, I guess, relatively friendly bacteria versus some other things you might find on the station. We have to make sure that we do some ground trials so we can test, and if we're using this medium and the agar, that it's the appropriate type. Is the container the right container? We've grown our plants in different types of containers. This is one of the largest tubes we have grown in. We've grown in smaller tubes. We've grown in plates, bit larger plates like this. I think they might be 3 centimeters across, little, or maybe 2.5, little tiny 35 millimeter plates. We've also, I guess those are maybe 5 centimeter. Or larger. We've grown them in the smaller tubes. We've even grown them in something called a magenta box, which is a box that has a little filter on the top, which you'll find in a laboratory. If you go to like UC Berkeley, it's just up the street from us here. Their lab. Hey, there's Bev, I think. Is that Bev?
It is.
Awesome. You found us on YouTube.
I did, because Michael stalked me and he sent me a message.
Oh, very good. So we're just kind of going through, and I don't know, I'm not keeping track of my time here. We're really kind of got a little funky this morning. Facebook was not connecting with us. Bev is one of our amazing educators from Southern California.
Whoops.
And we're finding ways to collaborate with her and others. And Bev, I don't know if you've actually picked up and selected what kind of legume, or if you know much about our legume challenge.
I don't. And now, well, I lost you for a second.
Okay. But if you stare right at where your camera is.
Okay.
I can see you now. Hey, Beth. I'm sure you're going to find your camera again. Look for that little
there
thing.
It is.
Blinking. Oh, awesome. Good deal. So Tony, can you pop back up the magnitude page?
Sure.
So I want to show the different plants. And Bev, I don't know how much you've known with Exolab and what we're doing, but I've kind of gone through a full cycle. I've been a little astray talking about some different things. I'm going to come back here and kind of go back to top of hour, if you will. I am kind of off kilter a little bit because we started about a half hour late. So those that were trying to find us at 7 o'clock this morning, my apologies. This is being recorded on YouTube Live, and I think you found us on Facebook. For some reason, Facebook for like almost 20 minutes was just not connecting, so we popped over here. We're going to be running another session this afternoon. I had promised to do one on YouTube and one on Facebook, so I can't see what we're doing wrong there with Facebook. Maybe it's just too many people trying to do it. We'll pop back in the afternoon, 1 o'clock Pacific time on our channel to kind of go over all this again if you just don't have time this morning. So what's happening? My goodness. So Magnitude is a company that really wants to work with students to go right to the very edge of discovery, right to the very edge of learning. And how do we do that? We run experiments in space aboard the International Space Station. We send a laboratory up there twice a year. At least that's our current pace. Our first mission went up in February of 2017. Our 7th mission is just being concluded right now. Literally, I think it was yesterday morning, the astronauts took our laboratory experiment out of our locker, took it off the data card, and put it in a flight bag and ready for it to be sent home. And so we'll get that back down here on Earth around April 10th. Our intention was to take it to a lab to do some sequencing. Our plant didn't do as well as we had hoped. It actually was stuck on the ground, and we got delayed and launched twice. And we were unpowered on that flight. And so etiolation, I'm going to get that word right eventually, but plants, what happens when there isn't any light, try to find it. And they're really smart, and it triggers activity in which it says, go try to find some light. And the genetics, it knows what to do. It fires it off and starts growing, gets really spindly and long. You might have had a plant you've been tending and it's in the dark in your house. If it looks really tall and long, it's not getting enough light. It might look a little pale. If you look at the structure, you took that plant and looked in the microscope, you'd see the cells were a little weaker, they were elongated, and they're not really as sturdy. This is kind of what happened to our plant on flight 7. So it got up there, didn't really have much of a fighting chance. It really gave it a good shot though. And it worked pretty well for the first few weeks of the mission as we had our ground controls here on Earth. So while we fly a mission in space, and our next mission is going to go up in August, we flew these legume. It's called Vigna, or think about cow pea or black-eyed pea. We want to fly a new legume using the same bacteria. And we'll talk a little bit about the relationship between the bacteria and the legume. It's really quite an amazing and extraordinary relationship. Without this bacteria called rhizobia, we would not really have a flourishing legume population of all these various beans and things like clover or alfalfa. So we need to find our next candidate over the next essentially month and a few days. We want you to get your favorite legume out there, support it, tell us why you think it's going to be a great candidate to go into microgravity aboard the space station. Each one has its own properties, different proteins, different density, maybe in carbohydrates. Nutrients are going to be different. How fast it grows, how slow it grows, how resistant it might be to being in the dark, or how much it can handle a hot temperature or higher carbon dioxide. I think most of the plants are flourishing with that high carbon dioxide level that we see on the space station. So these are our current flight candidates. Which team are you on? You may actually have a legume that your favorite legume, like a peanut. It's not actually a nut, it's a legume. It grows in the ground, right? It's harvested there. So maybe you have a legume you'd like to posit as a possible candidate. Build your argument. We hope for some academic research by our high school students and university students. If you're in honors biology, we expect you to do a report, right? You can have some fun doing it too. And if you get the right team together and rally the troops, who knows, we can actually fly your experiment for you. That's going to look pretty good on that college application, right? So put your best at it. It does feel a little weird not being in school, and it's kind of hard to kind of stay with your friends. And if you're like where we are in California, it's pretty much stay at home, has been mandated by our governor in order to stop the spread of the pandemic. And so it's tough. How do you work with your friends? Well, here's a great project, something to kind of keep you occupied. And maybe that level of the game is a little too hard anyway. And maybe you're getting a little bored with that other first-person shooter. So, right? Or Minecraft, you've done that enough, right? Come over here and try a real game of picking the right plant and actually getting it into orbit, right? Which would be pretty awesome. So the next 30 days, we're going to figure out who we're going to fly and why. We're going to then have our principal investigators, teachers like Bev and Steve and others will go through some experiments on the ground here to make sure we're validating this plant as being a great plant to send, and our protocols are done properly. We'll get the clearances from NASA. We'll work with our great team at Space Tango, the ones that help us get onto the station. And then we're going to launch. Our flight is currently scheduled for August 8th on SpaceX 21, launching out of Kennedy. And that's where they launch the big Atlas rockets to go to the moon. And SpaceX launches their rockets there. The double boom boom, or those things you watch them landing, that happens there at Kennedy. So that's going to be a lot of fun. And so you're actually involved in a real activity with a real mission in mind, but we need to find out what's going to be the best one to send up. So I don't know, Bev, if you've got some questions, but feel free to weigh in, jump in. I'm here to really kind of do a constant loop of what we're doing, and kind of going from there. I'm about to repeat myself a lot. I might get confused that I'm saying something more than once to the same group, but
Well, I think the obvious question at this point is, do we think we're going to be able to stay on schedule for August?
oh, well, even if we aren't, that's the amazing thing about space. We have to be at the whim here on Earth, definitely for our high-powered rockets and high-altitude balloons, and the super big rockets that go out beyond Earth. Weather. If the weather isn't good, we're not flying. We're not going to launch.
That's true.
Yep. And so that's number one. Number two, I think if you look at just the cadence of these larger infrastructures, you know, they're still drilling for oil out in the ocean. They're still harvesting food out in the fields. They're, you know, manufacturers, I think for the most part, especially if they're automated or doing their work. Retail, more the front end experience, the consumer experience. I think we're being impacted pretty heavily there. Researchers, I think there are many researchers that can collaborate at home. They may not be able to get access to their equipment if they're working on something. That may be an issue. I know there's staggered scheduling that I've heard that's happening, in which some employees will go into work and they're shifting up, and so some will be working over the middle of the night, so they're not they're keeping that social distancing happening. So I think people are finding a way. They're being very practical about it. They may actually even be doing testing in maybe some of your advanced facilities. Like you got a $300 million communication satellite that has to go up in October. You figure they're going to find a way to make sure that everyone's safe and they still stay on schedule. So it looks like I've got some text coming in here. Hopefully we can get those answered. And let me just check real quick.
Sorry, it's just Michael and I.
Oh, okay, cool.
Yeah.
And yeah, that's good. Yeah, so yeah, it's a good question, Bev. But I think for the most part, if we do have a delay in our launch, it will be something fundamental architecturally with the rocket itself. Now we've had rocket delays before because of propellant issues or some other mechanical. We've had countdowns right down into under a minute. It stopped us for a couple of days. In fact, this last mission I just mentioned, we were on the pad for 5 days with 2 delays for weather being a primary reason. I think the first one was an anomaly. If I recall, what they were seeing on the ground was different than what mission control was seeing, and that difference was that triggered we're shutting this thing down, and they'll do that. I mean, that's a lot of propellant, that's a lot of fuel. And it's highly explosive. It's amazing that reaction happens. We were talking about rockets a little earlier. A good rocket, about 90%, 5% of that rocket to get to space is just fuel. 5% is, and on a good rocket, is your payload. So imagine about that. That's why when you see the rocket going up, it drops the first stage. Get rid of all that extra weight, because I just dumped all that fuel into making power, making that chemical reaction happen, the LOX or whatever it is, the liquid oxygen, and that falls away. And so you've got less mass then to push yourself up to leave Earth's atmosphere. That second stage, after it burns up all that fuel, that falls away. You notice if you've ever followed these flights, oh, why am I drawing a blank here? The fairing falls away because there's no more resistance there, no more air that's resisting the lift of the rocket. And so the fairing falls away and you see the actual satellite or the payload that's going to be heading to the space station or going to go into deeper space or in a larger orbit. And then that breaks away. Now you just have the primary mission with the little fuel left for guidance and that last bit of push. So big push off the ground, drop that tank, another big push. And so it's really pretty amazing how that all works.
So I can potentially see like throwing this out to different groups of students, because I don't really know what my summer is going to look like, but I know that I talked to you that I was going to have a group of college students that are going to be right out of high school and they want to be teachers.
Oh, love it.
I don't know that that's going to go. I don't know what that's going to look like right now. Right now we're all online. Hopefully by the time that class is supposed to start, which is like mid or beginning of July, that things would be different. And, but I can see potentially like throwing this out to them as sort of a project to research and figure out, but also even right now, you know, we're sort of in a stage where, and I think all the schools are a little bit different, where the work is very flexible and where some work isn't even necessarily being graded, but we do have a lot of kids that are craving stuff to do. And I would love to like just throw this out for those kids, the kids that are just, you know, they're not the ones that are sitting on the video games waiting for mom to kick them off. They're the ones that are like wishing they had something else to do.
Well, there you go.
And I could potentially throw this out there and say, hey, you know, this is what I'm doing. And I could be, honestly, I could be doing the same research because I've never done this either. Right. And do it along with them and just see what I get. And I may only have 6 or 7 students doing it, but they will be into it, you know? So I kind of
fantastic. Well, as this is a unique experience, and educators out there, we work with teachers around the world. We have teachers in Africa and in Europe, here in North America. You have some unique challenges. You're looking at your scheduling for summer or for the fall, making plans for spring of next year. We can collaborate with you. We can set up separate calls. We can work through it. And so, Bev, for your case down in Southern California, working with CSU Fullerton, what we want to do is probably just convene a separate call, walk through what dynamics might be as if we couldn't physically hold a session. What could we do? Get them involved in this project. It's essentially, this mission is zero cost. We're not asking anyone to use hardware or anything like that. And oh my gosh, Dr. Barker. Oh, take us on a wild ride. So thank you for your email last night and for the introduction. And thank you for joining us today. We're going to go through, essentially loop through and focus a little bit more on the star of the show, Exolab. Talk about our legumes, but I would love you to chime in and give us what you can with respect to your knowledge on these processes. So for those on YouTube, and we've had some challenges with Facebook this morning live, so we're over on YouTube live this morning. Dr. Barker spent a good 3+ hours with us on a wild ride of all the possibilities and data science and these tools. And maybe if I can indulge you to share again with us a little later, some of those cool things again as a reprise, that would be fantastic. Dr. Barker works with plants in space. That's his love. And of course, it abuts a bunch of other things. Love of space includes rockets and planets and microbes, of course, and bacteria, these all interreactions, and even, it sounds reluctantly, an interest in mice because it got to be cataloged. He works over at the Gilroy Lab, probably the leading institution that's doing research. I think, if I'm not mistaken, primarily your research is with Arabidopsis. Is that correct?
Indeed, yeah. We're starting to branch out to a few other species, but Arabidopsis is definitely the workhorse of the lab.
Right. And very similar to Dropsilla, or like the fruit fly, or C. elegans, the worm. The genome has been fully mapped with Arabidopsis. And so if you're going to do any kind of plant investigation, that's a brilliant way to begin, right? Because you're going to be looking at these behaviors and hopefully being able to identify what's triggering those behaviors. Exolab, for the most part, we've been kind of macro investigating. We're taking this image. We've got some generalized data around carbon dioxide, temperature and relative humidity and light. Dr. Barker and his crew over there at the Gilroy Lab go down and look at the microscopic level on these proteins and the interactions and how things might be triggered with light, with the absence of gravity, or with different media, and all that's quite fascinating. And looking for these patterns and these relationships and building a hypothesis around this and then proving it. You can do that on Earth, but when you take that gravity vector away, things are just completely different. And how those genes express themselves is fascinating. And this role of inherited genes is just amazing to me. When we think about epigenetics, you had brought up the twin study, Mark and Scott Kelly. Our experiments, well, we've got 100+ schools, 130 teachers around the world on our current mission that's just got bagged up and getting ready to be sent home. While they're all here on Earth, they're kind of like the Mark Kellys. Mark was the half of the twins that was here on Earth during that study of almost a year. Scott was the other half of the experiment in space in microgravity. We have a plant in orbit in microgravity. So we're kind of like the Kelly twins, one plant in space, many plants on the ground, kind of as our control. The Kelly twins did something that we're trying to do here with our experiments. They ate the same food. They had the same sleep cycle. They had the same exercise regimen. So anything that changed, first of all, they were twins, so that was great, right? So if you have any expression that changes, hopefully you can correlate directly to the absence of gravity or some other kind of phenomenon that you could identify. And so that went on for a year, blood samples, and I'm sure they were breathing and they're looking at their eyes and they're doing all this stuff to try to figure that out. What we're doing essentially is the Mark and Scott Kelly experiment for plants, right? A little less expensive for sure. And we can do it more often, which is really cool. And unlike the Kelly twins, we actually have like 100, 200, 500, 1,000 experiments here on Earth. And unfortunately, we can't send that many to space, but if we could, that would be something we'd want to be able to do. Why don't I rewind back to the top, unless someone has some questions here to write in with me on YouTube. I'll talk a little bit about Exolab and how we've kind of set this up and what we're doing in a broad way. In fact, you know what I think? I left it in my car because I was taking a lot of stuff out of the office the other day. I'm going to bring back an actual piece of equipment that's been to space, and you get a little better sense of what it looks like. So let me just step out for just a second. We'll pause and have a break. I don't know if anyone wants to just chime in. Got Bev there, Tony, Steve, if you're still around, and Dr. Barker, feel free to chat for a second. I'll be right back.
Hey, Tony.
Hey, Beth, how are you?
I'm good. How are you?
I'm very good. Hey, you want to talk a little bit about your school district down in LA area?
You mean the college or the district, my middle school?
Yeah, your district.
Well, sure. Well, you know, I'm with Anaheim Union High School District. So I'm in a middle school. We are, as a district, we are low socioeconomic. I'm on the upper side of that, our district is split in a weird kind of funky way.
Oh, it's the puppy show.
Yeah, I know, he has to be here. See?
Oh, what's up, buddy? What's his name or her name?
This is Pee-wee. So he's one of the three.
Oh, there you go. These are your admins. Someone called them your admin.
Yeah, these are my admin. And yeah, I'm not doing a very good job apparently because they seem to be rebelling a lot and I'm getting reprimanded constantly.
Oh, there you go. They're just saying, hey, you're here for me. You're home.
I know. It's going to be so weird when this changes. Oh, this is going to be kind of like summer, even though summers I usually work, but
I think pets around the world are very happy right now.
They are.
Maybe some people are sad, but our pets are very, very happy because they're home.
Yeah, they're very excited.
This is one at home. They're happy.
Yeah, what's that?
I heard that dogs were the ultimate winners in all this, from unprecedented levels of people being home.
Oh, that's I believe that.
Let's go for another walk. Right. Awesome. So, hey, so this is a little cube lab, 10-centimeter cube. Looks kind of boring. A little room here for a fan. This would be where our connectors were for power and data. And this gets plugged onto a data card and gets slipped into a locker. And this is just a 10-centimeter cube. It's called, you think about it like a 1U equivalent. If you look at our Exolab, surprisingly, it's just about the same, but it's a 2U equivalent. It's two of these put together. And as I was talking about at the top of when we were starting, hey, Joe's, this is like intermodal transportation for space. So instead of a 40-foot container on the back of a truck that you see on the highway, 18-wheeler, or a bunch of train cars, and you see a cattle car and there's coal or whatever, electronics traveling across the country, or on a big ship, you can send something in a 40-foot container anywhere in the world for a few $1,000. I wish it was that cheap for space. But this is intermodal transportation for space. Imagine a 10 centimeter cube or volumes of this, so like a 20 by 10 by 10 or 30 by 10 by 10 or what have you. And it should weigh less than 1.33 kilograms if you want to keep it in that kind of characteristic.
I've got a quick question.
Yes.
Okay, so the size of the roads was determined by like the train carriages, right? And the carriages that were pulled by horses. And so basically there's correlation in all of the transport systems on Earth based on the size of a horse, because the horse was the first thing that humans started riding in. And so every time you go on a train or now even an aeroplane, there's like a symmetry, there's a mathematical formula basically that takes you back to the first horses that took humans around. So surely the same must be true for the space hardware. My question is like, the size of the...
I'm laughing because the answer is absolutely amazing. The answer, Beanie Babies.
What?
Beanie Babies. If you can believe that. So we have to rewind back to the late 90s. Stanford University, Professor Bob Twiggs, aerospace. His students are building an actual satellite, right? And it's the size of a small dorm refrigerator. Multiple years to kind of even build that. They're designing their own PCBs. They're sourcing their own sensors, making pretty much from scratch, doing their own programming. It's not really something university students have been able to do, right? It's all kind of really right at the very edge. And students are graduating before it's done. They're watching their colleagues kind of finish it and what have you. And so students are getting disappointed. Professor Twiggs, he's frustrated. So we've known Twiggs for a while now. He loves to drink soda. And we didn't know him during this time at all. We've met him much later. I'm pretty naive, kind of getting into all this, just really super excited about it all. But he loves to drink soda. So I can only imagine Twiggs holding up a soda can. Can you put a satellite in this? So he challenged his students at Stanford to build a simulated satellite. I've got one around here somewhere, in the volume of a soda can, called a CanSat, right? And so this, well, it just has an Arduino in it right here, but I have a sensor array that we build for students around the world where they measure different things. And so they built a simulated satellite for a fraction of the cost and fraction of the time. And of course, a fraction of the altitude. It was only going to go up a little bit. But what they did is they went out to the Black Rock Desert and they launched it in a high-powered rocket, 3-inch diameter, right, 6 or 7 feet tall, went up only about a couple miles. But when that CanSat, that simulated satellite, got ejected, it came down under parachute. It was about equivalent to as if a satellite had gone from horizon line to horizon line. Boom, shakalaka, right? They were able to, in a very short semester, get the experience and iterate on power, on operations, on communications. And so they were able to go through all the systems, EPS, whatever, in a very short time frame. And so this was a great start. And then he started thinking about, well, is there a way we can actually make small satellites? So another professor down at Cal Poly, Jordi Pugsiareg, and him began collaborating and imagined if they could make a small satellite to fit inside a rocket. At the time, and it's still, I guess, true today, in order to get the rocket science right, they've done the formulations, 95% of the rocket's fuel, 5% of its payload on a good rocket. You have to, your primary payload's never exactly what you need. So you need to add ballast. Water and sand was being launched. A great percentage of the mass to make your primary payload was water and sand. And Twiggs and Pugsiareg said, well, if we could make something small that actually met the vibration tests and the radiation tests and the temperature criteria, then, the shake and bake, if you will, if we could actually get it to work in a small form factor, then maybe we've got something here. So Twiggs is going around looking, and his wife apparently at the time was very interested in Beanie Babies. And there was an acrylic cube, a 4-inch cube in the store, and he picked it up and he goes, wow, that's probably going to work.
Awesome.
So it wasn't a horse carriage, right? It was Beanie Babies. And so Pugsiareg and Twiggs got this together, and they launched the first one into orbit. And of course, everyone in the industry, DOD et al., are going, you're putting debris in space. It's unconscionable that you're even doing that. how can you even get something that functions properly? There are now events in Utah. There's a small satellite conference. It's been going on for more than 2 decades for sure. And everyone from industry now, you've got various companies that Planet, for example, Planet.com, Spire, are all building their form factor off the 10 centimeter cube. So then what's the natural evolution of this cube was satellites in orbit, and we've got this thing on space station. Can we take this form factor, something that's been being standardized kind of on the fly, and it's kind of convenient that it's 10 centimeters, right? And it's got that kind of really consistent sense to it. And put this in a laboratory experiment and make it where it's more of a convention. And so on the satellite side, NanoRacks has actually got something called a P-pod deployer that's on the outside. The Canadarm usually moves it around, and it'll actually eject satellites from the International Space Station, drop them into lower orbit. Someone like SpaceX with their constellation of satellites will just launch a big rocket, and they have this huge rack, and they're just launching them out. It looks like a Star Wars with stormtroopers. I mean, just like, this folks, not stormtroopers, yeah, just like your clone army guys all kind of coming out. But it's just amazing where it's evolved. And so this is where the form factor came from. It's like beanie babies, not horses, carriages. So in this 10 centimeter cube, if we can fit in that, we are getting economies of scale. And to extend the economies of scale at Magnitude, what we thought we'd do is fly a single experiment, taking kind of the brunt of the cost in anticipation that many schools around the world want to join us. Invest a little bit. In this case, we asked the schools to pay the equivalent of about $500 to help pay to get us up there. And at Magnitude, we're basically saying, if we don't get that number that we need to fly, the price doesn't go up. Of course, what we need to do is get above that number so we can stay in business. And we've been fortunate to be just kind of riding right around that edge to allow us to do the next flight and the next flight. And so it's working for us, and it's working for our students. And so we're taking essentially 2 of these, filling them up with an experiment and sending them up to the lab. Now, it wasn't really designed for plants per se. It was just designed as a way to kind of make it work. But we have some very interesting properties, and I started to share an email with you, Dr. Barker. I'm going to take this offline and really kind of dive deep on it. But optimizing our labs for true research. Right now, we're kind of coming from the other end of the equation. We're both trying to build this amazing bridge. You're coming from the academic and research end of it. We're coming from the inspirational and an investigative curiosity kind of perspective. And hopefully we can meet in the middle where we can bring the excitement and the engagement of young minds to the advanced research that's happening on the other end. And some of the conferences we've been at, the big challenge there is intellectual property. And how can we protect the intellectual property of a researcher while still allowing our students to get the benefit of the experiment? So that's something we maybe talk offline, or maybe we just go on a little riff here a little later on about how one might approach that. But that's where we'd like to evolve. So these labs get us up there, and on Earth, we basically have created something that looks a lot different because we're thinking about how it's used in the classroom. And so that's the ExoLab, and it's a 2U equivalent, or 20 centimeters by 10 by 10, with a couple instruments on it. The back plane is a Raspberry Pi with Wi-Fi, and so it connects to a local network and then provides the data that's being gathered inside this box. On this acrylic cover here, it's got some screws in it, so it prevents kids from opening up and messing with the experiment, what have you, but it's clear that they can observe it. We'll talk a little bit more about the experiment itself here in a second, but we'll talk about the box for now. I'm gonna take this cover off. Inside, we've got an LED array. Again, these are all conventional off-the-shelf components in order to keep the cost very reasonable. These LEDs, we've made them to be adjustable in their frequency of light, of their duration, and their intensity. We kind of have them as set at a default that is equivalent to what we have on station. We have some teachers that are very interested in looking at variation. And since we have so many systems out there, we actually encourage them, if they want to explore with different things like duration or intensity or wavelength, they can do that. And if they want to see what other plants are in the network, maybe Tony can share with us our platform and how you can look at all the different plants. These guys generate a little bit of heat. It'd be nice to find something that didn't generate so much heat. That kind of, I think, affect us a little bit. Underneath here, we've got carbon dioxide sensor?
Oh, for the heat thing, so NASA created a thing called the spectrum analyzer, and they also have illumination from above like that. So what they did was they just had a piece of plastic, just like a centimeter-ish away from the LEDs, and then a little mini fan next to that. So just to kind of catch the heat that comes off directly, and then just kind of like suck it away.
Right.
I don't know if you can blow out into the station, or whether you'd have to circulate that heat within the CubeSats. But that is a possible mechanism.
Yeah, I'm going to dig up a diagram here that shows you what our labs look like. And so we've gone through, well, every flight has been a variation on fan design. And in our earliest designs, honestly, Dr. Barker, I think what we were doing is we're pushing a ball of hot gas around. I think that's what we're doing. I can just imagine, you know, like you see like the beach ball with the fan and just kind of spins in the air. I'm envisioning that was what's happening with our heat. It was just kind of rotating around. And there are other heat sources in there.
I wonder if there's a way to see heat in the air. If there was like a temperature sensitive dye that you could just mist up into the air and just blow that around.
There you go. Well, that's possible. Yeah, and I guess if you had, you know, one thing you might want to do is actually fly no plants at all and just run thermal experiments. And if you really want to talk about more of the engineering side of this equation and optimize. And so what we're doing is kind of, in addition to learning more about everything that we're doing here collectively with our schools and teachers and students, working through a challenge of engineering and a challenge of biological investigation. So we're probably complexifying, I like that word that I've made up, too much, but love your input on that and what we can do to optimize it. Cooling systems, there's actually a cooling system that you can plug into these things. Apparently the adapter is like $45,000. So we're kind of like, you know, got the hat in hand there, trying to look for someone that wants to raise the funds for that. But if we can get a locker that's got a cooling system, we can bring it back to a much more reasonable low 20s rather than high 20s, right? Celsius. So we've got the CO2 sensor. Turn it that way. The sun's coming right through my window here. CO2 sensor. There's a little pinhole. It's kind of hard to see here. Just above that little bar that's popping out with the temperature and relative humidity. This bar that pops out is a light sensor measuring micromoles per square meter. It's an I²C port, so I can actually pop that out and I can daisy chain other instruments terrestrially here on Earth if I wanted to add maybe infrared, spectrometer, microscopy, whatever. Something we might want to add a different gas sensor could be done with some engineering investigations, which would be kind of fun, I think, for some students to do. The challenge there would be we'd want it to be scalable across all networks. So if anyone wanted to be able to add this adaptation to their classroom, that we could do it without saying, hey, everyone's got to buy a new piece of equipment, right? Now, you know, the veggie and growing beyond Earth and what they're doing in the classrooms, if we think about this backplane here as the functioning part of ExoLab, I see no reason why this couldn't be the brains of a much larger, say, half a cubic meter veggie equivalent, right? Measuring your gases, taking an image and what have you. And so that's something that could be explored as well. But we keep in this form factor right now because that's pretty much, you know, what our boxes look like as they go up to try to give us a clear sense of what's happening in
it's surprising they don't have those sensors on the veggie, to be honest. When you get back the data from that and it's a bit hit or miss as to what they provide, like having that integrated system like predetermined like in the way you have is a really good thing.
Mm-hmm. Well, thank you. Yeah, I know for imaging, one of the restrictions we heard straight away, because we were talking to Trent several years ago, it's kind of been in these conversations, is privacy. That because it was in an open out there in the lab, it wasn't in a locker somewhere, that, you know, astronaut time or other experiments were being captured by an image. So we need to position in such a way, like you've got the curtain that kind of comes down, maybe have a camera over the top that can be worked on. So I'm going to segue just for a half a moment here. There's something we're working on with NASA Ames. It's a robot. It's a 30 centimeter cube. There's actually 3 of them up there. They're just now being commissioned. They're called AstroBees. And the AstroBee is designed to navigate through the station and do different things. Eventually, I think they're seeing it as a tender for the deep gateway and keeping the station operational while humans aren't on it. Well, they might be away on a mission on the surface of the moon. They might be heading to the station or back to Earth or to it. And so these tenders are a possible investigation of things that can be used. We wrote a proposal and we've been accepted. Now we're doing, in terms of the general concept, we're now going through the formal proposal now to put a digital nose on that robot. It's going to sniff around for the gases in microgravity, since convection doesn't work the way we expect it to, like here on Earth. And, it's all different. And that's why I asked you yesterday about, do these the bacteria, do they smell? Right.
Yeah, because
So we pick up signatures, right? But the idea with this is it also has cameras on it, and you could probably load out things like infrared or ultraviolet or other things like that. And we could send, these things will dock on the wall and recharge and basically do their data dump. You could do Wi-Fi as well, and if you want real-time telemetry, but we don't need the XYZ axis positioning. We'll rely on the navigators, their aims to take us on our missions, our little sorties through the station. But I could see it kind of undocking, going over to Veggie, taking an image for that hour, going and doing some other missions, coming back, taking an image again. So in a way, kind of engaging the experiment without interrupting the astronauts, because it was its task. It was programmed to go over every few hours, take a picture, do a sample, whatever. It's a robot arm. Stanford's got a gecko gripper arm they're prototyping. If you zoom in and look at the mechanical connecting points, it looks like a gecko's foot, right? With little kind of hooks on it to kind of grab things. Bosch has got a little sensor that detects different audio frequencies, different arrays, like 1,000 hertz or 5,000 hertz or 500 hertz. And they're listening for sound anomalies, basically building signatures of sound on the space station. Something I never thought about is the noise levels on the space station, right?
Yeah,
you have to keep everything below a certain dB. And if it gets cacophonous, you can't leave it, you can't escape it. And that background noise, that drumming noise, I imagine at a certain point becomes unbearable, especially if you're up there for 6 months or longer. So noise levels are really a big part of this.
Did you
so
know
all these experiments all get connected?
Did you know plants can hear and feel vibration? So
I do. So yeah, I have a book around here I've read more than a year ago. And I think it's something like Plants See or Hear. Or what's the title of that? It's actually fascinating.
The reason I mention it is so the space station is a multifactorial environment. We know the microgravity, we know the radiation. Everyone always overlooks the vibration. So there's some recent work that's come out of South Korea where they've been looking at the effects of vibrations on plants and gene expression. And there are certain vibrations that cause the plants to activate the defense system. And as we were going through this study of theirs, we found a frequency that looked like it was activating a pretty extreme defense response in the plants. Wow. So we mimicked it. The plants all died. There's a certain frequency of sound and vibration that you can play that cause plants that are exposed to it to just die over a couple of weeks.
Herbivores footprint pattern, right?
Possibly, right?
Right.
So
here comes the cows. Here comes the dinosaur, right? The brontosaurus is going to eat us again.
But there's no sound or audio recording or vibration recordings of the ISS. That you can find the occasional things through YouTube, which have been distorted. So if there was a true recording of the vibration on the ISS, that would be really helpful and interesting for this particular avenue of research.
Now, vibration, there's sound vibration. There's also things like, I guess, accelerometers can give you vibration as well, right? But I don't know if that would be what you're looking for. It sounds more like sound vibration rather than, let's say, acceleration, right? Like if something's vibrating, there's a change in position, right? It's like a diaphragm, like on a speaker.
Exactly that. I guess the main requirement would be the file format would have to be accessible by media players, so you could just play it through a speaker to replicate it in the lab, to then use the space station audio recording as a stimulus in the classroom.
Wow. So I'm going to tease a little bit here live to everyone. We're looking on a semi-permanent installation on the space station, but biology is a very difficult thing to include in that. But I can imagine a sound study in which what's about the semi-permanent installation. It's designed to be a classroom in space. and it can be rebooted and run over and over again.
There's another really cool experiment that having a speaker up there would be able to manifest. So we've seen the videos of the roots going off all over the place because there's no gravity vector to direct them.
Yep.
There's a recent study from a university in Sydney that has shown that the roots grow towards an audio recording of water flowing. So there's something in the sound.
Get out. Really?
Yeah. It's peer reviewed and published like last year or something. So
wow.
A wacky theory that I would love to test on orbit would be having like a speaker below your samples and playing like the sound of water and seeing if the roots grow down towards the audio recording in the absence of the gravity.
Oh yeah. Wow. Yes.
Write that down.
It's so easy to say yes, Dr. Barker. You're so deep into this and you know where you want to go next. And we're just scratching it from hey, we're curious, we're looking at this. How can we make sure that we adapt it to the classroom environment, right?
The problem with this experiment I just mentioned, though, is you have to have the initial recording of the space station for like the preliminary data for you to propose onto NASA. That doesn't exist, so hence I'm voicing it. The other concept is having flight certified hardware to go up through conventional like NASA proposal is difficult. There's a relatively limited selection, so you tend to focus on what is available and what is pragmatic.
Yep.
But if you have the capacity to put stuff up and have been prototyping in that area, then it's not a crazy thing to ask or to say like, hey, a speaker in there to direct the routes. Right. For us to say that to NASA, that's like 10 years of like product development and testing, and it would just never fly through their proposal system.
Yeah. Wow. Yeah, that's amazing. Yeah, I believe at a very high rate of iteration. It's like, just do it. Figure out all the things that are broken and all the things that work, and focus on the things that work and make them better, and get rid of the things that are broken or find a way to solve those problems. So sound is, if it wasn't disrupting our primary investigation, or maybe that became the primary investigation. So where we are right now, and Dr. Barker, I encourage you to kind of work with us in a more collaborative, deeper way beyond this mission. Our Leguminauts, our focus challenge here is to select some legumes that we're going to down select to pick one to fly on mission 8. We're kind of locked on that. Mission 9 is in February. Mission 10 will be fall of next year. There may be a mission during the summer, 9.5, or maybe it is 10 and 11 happens in the fall. So we've got this cadence that if we jump out 6 to 12 months, we can consider what that might mean. And what's nice and what I like about your offering here of ideas is I know it comes with a deep-seated understanding of what exists today in the world of investigation and plant biology, and interest around these effects of microgravity. So I encourage you to make a laundry list of crazy, cool, fun, funky ideas that we can consider. And for you to come join our principal investigators when we have our regular convening and talk about, we're getting through this legume challenge right now, but talking about the future and some selected missions we may consider. And from that, and working to making it real. But yes, let's do that.
That's awesome. And like, this is one of like the most important lessons in space research, is the concept that these plans take so long to manifest. There's so much pre-planning that comes before. And so that's why we have to like really like think deeper out and think long-term. Sometimes it's that long-term game that students don't like to play. A lot of people want that quick kind of positive feedback, the quick gratification that we get from computer games and candy.
Right.
But the real satisfaction in spaceflight biology comes from these like really long, drawn out, high-end dreams, right?
Right. And that's super important. And so help us navigate. Right now, we just kind of pointed to the horizon line, but we may need to make a 90-degree turn here and orient to that horizon line where the research, the edge of research is happening. There at your lab at Gilroy, there in Wisconsin or in other places, where we now can tune in, if you will, to the relevance and have that aligned pedagogically to what we're seeing in our high schools and our middle schools and our primary schools, where fundamentally it makes a difference in those classroom environments, but it's making a difference on the research side as well. This is what we want to be when we grow up, right? So let's do it. That's wonderful. So this is our ExoLab. It does take an image once an hour. I think that's the last component I didn't mention. This wide angle image, in the classroom, this little LED will flash a minute before it takes a picture for our camera shy folks. They can pretty much shelter in place it's like while it takes the picture. It's kind of hard to see things really beyond the scope of what's inside the lab, but I think if someone wanted to run up and put their face in there, you'd see it. For those really concerned, we do have in essence, a privacy screen that can cover the lab. If you're looking at lower light conditions, it doesn't block all ambient light, but it does a pretty good job of blocking out most light if you're running a low light experiment. So that's good for that as well. So that's kind of like what we did with ExoLab, as just like, let's get started. 7 missions with this, going on mission 8 here with our legume challenge. And what do we have in the lab itself? So let me put this off the side here and look at our current experiment that's just got packed up and being sent home. Now on station, we actually had 3 tubes, 2 controls on the side and a center tube. And here on Earth, we had much larger tubes. These are 38 millimeter by 200 millimeter tubes, so they're fairly large. This one right here is a pretty good candidate here. We can kind of see the inoculum. I don't know if you can see that there at the roots. And this was planted on February 28th. And development of the leaves here. And again, my lighting's not, the sun's kind of coming into a weird angle right now this morning. And so this is with the Rhizobia inoculum. And basically we had the control then with, and this looks like really nice root development too. Beautiful. This doesn't have any bacteria in it. Things we might want to try, since this seems to be growing pretty well, is maybe actually adding back the bacteria in now, or mixing the bacteria and agar as opposed to coating the seed with the bacterium. And those protocols, I'd welcome your input on that, Doctor, on how we can kind of optimize that. So that legume Vigna with Rhizobia, they're doing their little kind of barter, right? Hey, I've got some nitrogen. Hey, look, I got some carbon. Plant through its photosynthesis is giving us that carbon for that little equation, and the bacteria is doing a really good job of making some extra nitrogen. And as I understand it, and please jump in and help me with the anatomy, this is all happening there at the root structure, and I'm not quite sure the mechanics, but maybe you can explain it to our audience here in more detail. In fact, I should probably just turn it over to you, but let me explain it so you can correct me on all the things I have wrong. In that exchange, these nodules begin forming where that nitrogen and that carbon is being exchanged. And if you cut it open, that really kind of pink, healthy exchange is kind of like a hemoglobin, if it's not even hemoglobin, of nitrates and nitrites. Ammonia is all kind of there for the plant to use. And everyone's happy. The bacteria is loving it because they're getting their carbon so they can grow more, and the plant's loving it because now they've got this source of nitrogen where they can flourish. And I understand because there is a net plus on the nitrogen side, this is why we have our legumes as green fertilizer. Essentially, we turn them back into the soil. That nitrogen's now, we've enriched our soil with that, and our next crop we want to plant will be able to take advantage of that. That's a layperson's explanation. Please correct me, Doctor.
No, that's all spot on.
And can you maybe to dive a little deeper and help us understand mechanically what's happening there?
Yeah, there's a really interesting moment when the rhizobium first encounter the legumes, when they're in like the soil around it. Essentially, as the root hairs detect like the bacterial cells that are next to them, there's what we call a molecular dialogue. Molecules move back and forth. The
molecular dialogue.
Yeah, and it's very specific. Like, as I'm sure teachers are aware, there's like certain specific rhizobium varieties that like certain specific varieties of legumes. It's like it's a very like host specific relationship that they form. And so my doggy Savannah is pestering me. And so they produce these very specific chemicals called nod factors, and nod factors move back and forth, and both the plants and the microbes have evolved different varieties of nod factors that move back and forth, which they then recognized. When they recognize this nod factor, this is what then causes the differentiation of the root hair cells into nodules, which then start to swell. And you are right, that red is a heme. It's not hemoglobin, but it is a heme protein. So it's this very similar kind of molecule. And plants actually naturally produce this. This is one of the ways they control their metabolism in regard to their chloroplasts and mitochondria, because there's different stages of the day when they have different demands for oxygen. Somewhere there's more and somewhere there's less. And so there is this like temporary storage of oxygen in these heme molecules, which is in the cells, like floating around. It's just that the relationship between the rhizobium and the legumes has kind of co-opted this molecular mechanism and then evolved it to be even more beneficial for the pair of them. And so understanding how this communication works in an environment where oxygen movement is different, it is really fascinating. Yeah, it's a really exciting area.
Interesting. So just by putting us in an agar medium, we're fundamentally changing this communication, this dance, right?
Potentially, yes. We're not sure. So there's a lot of people that have done research on this type of relationship in agar. So it's totally normal. But then all the good old-fashioned agronomists would say we have to do it in the field. But
right.
Our field station is 200 miles or 300 miles up. So sometimes we can't use soil. So this is the nature of spaceflight biology.
Right. And so that's an interesting thing. And I'm a little frustrated. Oh, it's interesting. My camera, if I pull back a little bit, I lean back as opposed to lean in. I like to lean in when I'm talking. I'll lean back and then the lighting's a little better. That we don't actually fly our plants in a soil environment, that we're flying it in an agar or flying it in these pillows, right? Or something else like that, like veggie, these, and
the pillows are essentially full of clay. It's called arsolite.
Yeah.
It's the same material that people use for baseball mounds and for people who do bonsai trees.
Yeah.
Clay is a fantastic medium. It's got this like these sheets of material which hold ions in them. It's a cation, has a high cation exchange capacity. So you can imagine like a book, and you have all those different layers of paper. Well, clay has those like layers going through, and so when water goes through, it can take in nutrients, and those nutrients can be deposited on that clay, and then they can be removed later depending on the pH. And this is how the plants release the nutrients. They can exude ions, they can exude and to change the pH around their roots. This creates what we call the rhizosphere. This is what helps or hinders microbial growth in that area. And so arsolite is the mechanism that NASA have been using to provide as many of the characteristics of soil as they can without actually having dirt up there, because well, they want to keep the station as clean as possible.
So yeah, and when you look at something like arsolite and you look at the regolith, the composition of the lunar surface or Mars, they're still fundamentally quite different, right? Like the Martian, at least the simulants that we looked at, they're quite hydrophobic.
Indeed, and then the structure of it too. Like when you get the Martian regolith simulant, it's generally been ground to a powder. And so this is one of the things that you then, why you start to appreciate soil. People don't appreciate soil enough. It's wonderful. Like the heterogeneous nature, how variable it is. You get big pores and small pores, you get clay, and you get sand and silt and all that organic matter that glues it all together in various different random ratios, depending on where you dig it up from. But when you get like Martian simulant, like regolith from like the top of a mountain in Hawaii, for example, when it's the best spectral analog that we have. But at the same time, when we extract it, we end up making it really uniform by like grounding it up to become a powder. And then that in its own right creates what I would call an alien situation, because in the field, plants have never encountered like a finely powdered clay stone before.
Right.
So this is when, so if you ever get a chance to play with that lovely regolith simulant, you then really
have some. Yeah, and I was kind of frustrated. I was trying to mix it again, this like naive approach to this. Let's try a 90-10 mix, a 10-90 mix, and a 50-50 mix with agar, and to try to create some kind of slurry. And can we boot a protosoil up or something like that was my thinking, and it was just a mess.
we were able to get plants to grow in it quite well, actually. The thing is just the structure. and water retention. When you have a powder like that, you get the slurry effect. It doesn't hold the water there. So just by mixing in vermiculite or perlite, the classic thing a horticulturist would do to increase water retention, you can then essentially grow plants in it. And there's a group in Holland that recently did this and were able to get worms to live in it too.
Get out. Where you say this was Holland?
Some Dutch research team.
Now that is cool because they're going to go through but are they getting what they need out of it, or was it just like, hey, look, that can happen, but they're not going to live?
They can live, but then you do need to add the organic matter, so the things that they're searching for.
Right.
So you could take the regular stimulant and you could increase the water holding its potential, so you can grow plants in it, and then you could introduce other organisms such as the worms to swim around.
There you go. So here, just to kind of bring us back a little bit to our hope with the teachers that are out here, they're watching this either as a recording or live with us. If you have questions on YouTube or on Facebook, please write them in. Hopefully, I think we're having a regular team meeting right now. It's our standing call at 9. Our team will be joining us probably around 9:30. But and they can look for your questions and answer them. But what we want to be able to do on our next mission that flies in August is to select an ideal candidate legume with the proper rhizobia to send to the space station as a follow-on to the mission that we're just now concluding, which as a precursor, we flew a couple different bacteria to see what they might do. Rhizobia and Azotobacter were the bacteria with an E. coli in a control. And so these are our candidates right now. And there are many different approaches we can take to this. At the end of the day, we're going to heavily weigh on the scientific merit for it. But really what we also want to be able to do is explore and encourage the artistic side and the creative side of this investigation. We're in uncertain times. I mean, the reality is about a week ago, I guess, I got our team together at Magnitude and I said, we need to do something. Schools will be shutting down and teachers may need to have something they can share with their students, or parents at home with their children need something that can be fun and engaging. How can we connect the world? Well, since we have the International Space Station, with more than 120 countries having run experiments up there, and more than 18 countries actively involved in investing in the architecture and making it work, that the International Space Station will be the perfect lens in which we can look at bringing the world together. And in a way, this pandemic is bringing the world together, right? Which is really kind of wacky, and investigate these things. So creativity to me and having fun during these times, during this challenge, is just as important. So here's a mission patch that we developed for our last mission, and it was all done in-house, and it looks all corporate and neat, and really talks about what we've done. It's a nice, embroidered patch. But I would like our students out there to design our mission patch for our mission when it's ready to fly. And I want you to have fun and be creative about that. And judging.
One of the games that I often play with students in the class is the acronym game. I'm not sure if I mentioned, but or you notice all of our studies have got funny names like toast and mango, and these things are all acronyms. And NASA loves acronyms. If any of your students are going to work for NASA in the long run, one of the things they're going to have to do on a week-by-week basis is not only learn other people's acronyms, but also make up their own.
There you go. I want yummy or tasty, guys. Can you make an acronym for me, right? Delicious. Exactly. Oh, that's a long one.
But that has to also be relevant to the experiment too.
Exactly right. Well, we're talking about food here, right? Nutritious. See what we're looking for.
Liver, legumes, orbiting, something Earth regularly.
Awesome. Hey, Lauren and Michael, thanks for popping back in. And I guess you've actually got a guest with us. Turn this off here and share your guest. Look at this. Oh my goodness, those are beautiful. And how old is that plant?
This plant is about a month old. This was one that was extracted from the growth media, in the and then planted in a what do you call it? Water bottle. So just cut the bottom half of the cut the water bottle in half, stuck the top half down into the bottom half. This becomes a reservoir and a funnel. So there's a hole and some cotton string in here that goes up into the potting media. And that's just a mix of vermiculite and sand and soil. And see, it's blooming and we have fruit.
Oh.
Now help me, Richard, you're on. So they're pods on legumes, not siliques. Is it silique, a pod that's not a legume? How's that? What's the taxa there?
You just got it spot on. Yeah. We'd call them a pod on a legume because they're slightly bigger. But when we go to a brassicaceae variety, like the lettuce, I like mustard and Arabidopsis and my favorite models.
Yeah.
There we call the seed pod siliques.
Right. And if you look closely, you can even see there's some developing. Well, they're not ovules anymore. They're now seeds developing their embryos. So you can see the little bumps on the cross section there. And we'll uproot this one later today, not to kill it, but to harvest a little snip of the root, and then I'll dissect we'll point out the nodules and I'll dissect them and give you some nice cross sections so you know what you're talking about with your students. But I think that the legumes have some of the most beautiful flowers. They're that kind of orchid shape, and these haven't opened up yet, but they've got a beautiful white sail, and they have ultraviolet markings on them to help the pollinators target in on the center of them, but they show up as a white on white. So it's, yeah. So it's not Audrey, but sort of Audrey, one of Audrey's cousins.
I would love,
podmates.
I would love to see the UV photography of those flowers. Like I found a meme online the other day. It had a couple of them, and it's just amazing how beautiful like the
Isn't
insect
is. I wish I had UV vision like the bats, but then I wouldn't have a cornea, and then I'd risk retinal cancer. So that's probably not such a good thing. My eyes are enough of a mess as it is. But some of you might not know that Monet, if you look at his body of work from when he was young through like real maturity, over the period of, I don't know, it's 2 decades. I'm not an art historian, but a couple of decades, you start to see the work gets muddier and muddier and darker.
Yes.
And that's because he was suffering from cataracts.
Yes.
And the solution was to remove the cornea. And then just like instantly all his work becomes like surrealistic, vibrant. And that's because he was actually seeing the ultraviolet. And that's what he did, is he painted the colors that he saw. So you can really see that transition, and you can get a sense of what ultraviolet vision might look like that way. But I do have an ultraviolet light around here someplace. If I can track it down, we can try to get some images of these flowers. But that's something, at home, if you've got access to that, a little ultraviolet LED, and do some photography with it. It's really cool.
There you go. Now, Michael, if there's a way we can add an ultraviolet light to the ExoLab.
Oh, wouldn't that be cool?
Now, just that I2C port, right? What do we need to plug in there? So that's a design.
I want some
challenge.
infrared in there too. I got a FLIR. I'll take some infrared photography. You think we'll see any complaining in infrared, Richard, when I snip some roots? Or do we need the fluorescent in there to see that?
Yeah, we might need to. You're on mute there, Dr. Barker.
Sorry, my dogs went crazy because FedEx just arrived. I miss them.
Okay.
But
your lifeline.
Hi, Savannah.
Sorry. UV illumination is really awesome because it's kind of like fluorescence. You excite the plant with a particular wavelength, and then the plant will emit a different frequency of light. The classic example of this is chloroplasts. Chloroplasts are autofluorescent. And they so when you shine blue light on them, if you have an infrared camera, you can do what we call NVDI, near vegetative diffraction indexing, and you can essentially have a filter over an infrared camera that prevents either red or blue light going through. You can look at the infrared absorbance versus red or blue, and essentially you can start to measure the natural fluorescence that's occurring from the plastids. And this can actually be an indicator of stress before you see stress. So if you provide a plant with a pathogen, and the pathogen is designed to go through the plant and attack it, you will see the autofluorescence of the chlorophyll switch off before the pathogen gets there. So on the South Pole in McMurdo, actually I think it was with the European Space Agency, they've built a shipping container where they've filled it with plants in order to demonstrate how much food they could produce on the moon in such a formula. And they have used this NVDI imaging to monitor the plants on the South Pole so they can kind of intervene remotely. It's a really simple technology, and it has a lot of potential for use in agriculture, both on the planet and off the planet. And again, it's illuminating the plants with normal light has to be consistent between your samples. And then essentially just having a blue or red filter in front of your infrared PyCam. There's a range of websites that have DIY mechanisms for both getting the photography and processing the images.
So I don't want to use the infrared, the FLIR outright. I want to filter that.
So by using the no-IR PyCam, you get all the color plus the infrared coming down onto the RGB sensors. So by then putting a red or blue filter over the camera, you remove the red or the blue from the image, and thus the infrared the infrared energy gets absorbed by either the red or the blue CC.
Oh, gotcha. So I wouldn't actually need an infrared camera then to see that.
So you could just do it with one of those normal Pi no IRs.
So that is, by the way, a normal Pi camera that's on there.
There it is.
Yeah, exactly. That's why I thought you might like it. Because so you would be able to see the plants being stressed and where the stress is before it gets there. I've got a video of it that we made once where we added a plant pathogen. It was penicillin, and like 24 hours before, you could see this wave of fluorescence going across the leaves. But as then over the next 3 or 4 days, we saw the penicillin take that same trajectory. So NVDI, it's a fascinating technology.
So just a question about that.
Hi, Liam.
Hi there. I think the camera is actually, if it's the regular one, it's not the no IR one, which I think is what you would need. And would you really need it as a video, or can it? Because the images are only taken once an hour currently. So
I prefer just the still photos. It's quicker.
Yeah.
Oh, yeah.
Okay, and how frequently would you need it really to be able to see that type of change?
Actually, once an hour would be really good.
It would. Okay. All right.
Yeah, it really would.
Well, I wonder if the iPhone camera would work, because they put an IR filter on that after the first one.
Possibly. I've actually been intrigued by the concept of getting access to like the industrial iPhone cameras. They're like, because if you can imagine, if you could get them in bulk, you could get them quite for a good deal. And their resolution is higher, and yeah, you know. But as it is, the PyCam 8 megapixel is a fantastic tool. It really is. It's a game changer in the world of research and education. And so it's amazing the new things, the new opportunities it's creating, and the way companies like Magnitude are using that to inspire the next generation. Like, so the thing that we're doing here is project-based learning with the biology. Some people really like the engineering side of it. I'm a biologist, but some people do like the concept of design and build. And the Raspberry Pi ecosystem has created a modern Lego lab for people.
Exactly right.
Like in the olden days, these things that used to be so expensive to make and just impossible. Like, and now you can do it at cost. It's brilliant.
Speaking about hardware, well, this is more about Docker. Can you send me the specs on what you need for the Docker, and I'm gonna reach out to the network and see if we can't find someone to help you out there.
Awesome, thank you. We'll do.
Totally separate, but I was halfway through writing that message to you this morning, and I realized it was almost 7 o'clock. And so what's interesting, as we flip from Facebook to YouTube Live, apparently my got a lot of folks watching, but my comments are turned off, and I don't know what I've done I might have to stop this stream, but let's just keep it going this time. We're going to figure that out. working through our bugs. We got 34 more days. So by week 2, we're going to be looking pretty awesome. And Lauren Parker has joined us. She's one of our principal investigators as well out of Texas, working with us on figuring out what we need to do. Oh, and your buddy. Hey there. Hi, Lauren.
And Lauren,
So
how did you do that awesome space thing with your background?
Hey, stop. It's just my coworker is not happy. If you look at the bottom of your screen where it says stop video, there's like a little carrot pointing up. If you click on that, you can add a virtual background. Michael's actually much better at it than I am.
Ooh, cool.
It works better with a green screen than with my red wall of my kitchen here, but you know, hey, we're doing.
And some of it depends on your processor. Sometimes it doesn't allow the virtual background. If you have a really recent processor, it actually allows you to put a video behind you as well. So, and
I think my little MacBook would fail that test. That's why I've got the ISS above running right here.
No, that's because you've got you've got a nice clean background as well. You cleaned up your background.
Yeah,
sorry, I should switch.
You didn't see my garage before I had to work here.
Yeah, there you go. So and it is fun if I just
really quite a mess.
If I switch on the virtual background.
Hey there, Liam. Good morning.
This is so now. Oh, why has that not come through yet?
I see it.
You do. Okay. Yes, you do now. There you go.
We'll
see, and it's better if you don't have headphones on.
Yeah, it's
or a spaceman suit.
Yeah,
there you go. The next meeting, Liam, I expect you to have a helmet on.
Yeah, there you go.
All right. Anyhow. So, Lauren, what plant have you been responsible for? We're looking at our legumes.
Going with Team Chickpea.
Chickpea. Oh wait, hold on. Protein.
Protein power. Yes.
Have you thought it? So, teachers, students, we're riffing a little bit here, but really the key challenge is to keep our students engaged in a curious way to something extraordinary. We want them and we want you to help us find the right candidate for our next mission. We're focused on a legume. We've got a lot of different ones we want to look at. And we have our different teachers that have been working with us that are kind of taking on that role and responsibility to kind of get behind the legume. And they are looking for support. And so I'm gonna put you on the spot there, Lauren. Share with us chickpea and some of the interesting characteristics why you're thinking might be a good candidate.
Well, so chickpeas, number one, they're delicious. You can eat so many ways. I mean, if I'm in space, I want something yummy to eat. And so chickpea to the rescue there. You can mix them up, make some yummy hummus, little pita bread, have a yummy snack. They're also really good roasted. And so, you know, I initially picked chickpea completely on a taste factor. I would
super important.
Eat a chickpea than a green pea, and so that's why I started with that one.
Any day of the week.
So in looking at some of the growth characteristics of chickpea, you know, we're going to have to kind of look at some media things. They don't like to be too wet. They like what they like, and that's about it.
Oh, they're sensitive.
So they just know what they like. So,
so we would have to maybe make an environment that was really making the chickpea happy and comfortable.
Do some environment to help our chickpea friend here, but lots of good nutritional value, lots of folate as well, in addition to the protein power. So it would be a nutritious food source in space and doesn't take up a whole lot of room. It's very nutrient dense.
There you go. Well, I've got Team Adzuki, and it's supposed to be a nice weight loss bean. At least that was research done by some company I think was selling weight loss stuff, but I'm gonna have to do more research. But I like it just because, again, going back to the food, you know, I think one of the first things the astronauts do when they've got a mission as they go to the lab to taste the food, right? To determine what their meals are going to be like. And if you don't like the food, it kind of makes everything else kind of tough. So yeah, I think taste is a super big important part, and I think that's kind of qualitative. I guess we can add seasoning and what have you. But it definitely, I think it's one of those categories that we're going to need to consider. Does this thing taste like poop? It's like they probably don't really like amazing proteins or whatever, but what can we do?
I've got a story about that.
What?
I've got a story about that from.
Oh yeah, well, let's hear it.
So they did a test on astronauts using algal wafers. So algae is brilliant. You can grow it in space, and you can modify it to have all the essential micronutrients that you need. And it's very efficient, particularly in an environment where plants experience a flooding stress. You can imagine algae would be a great crop. So they then made some algal wafers, and they tried feeding it to the astronauts. And astronauts will do anything to go to space. You could say, okay, you can go to space, but we're gonna have to cut off one of your legs because you're not gonna fit in the spaceship otherwise. And they'll go, I've got to go up there. It's what I'm here for. It's my mission. It's for people, humanity. And they'll cut off the leg and they'll go up into space. Astronauts are heroes. But when they go up in space, they don't want to eat algal wafers because when have you ever eaten an algal wafer on Earth? Right? It's a true story, and it's entirely based on the US Astronaut Corps. I'm not bringing the JAXA, the Japanese Space Agency, into this because their culture has traditionally eaten algae and variants on that for a long, long time. So they were more perceptive to the idea. But yeah, so flavor and texture and normality is important when considering what the astronauts are going to want to eat.
Now, I guess preparing your food in space is something we haven't considered. We're just looking at the growth right now, but that is definitely going to be a part of it, how we can make something taste a little better. Let's see, we've got Michael, are you responsible? You are Clover. And you've got red and white, or white, and white.
I've got red. The white I could only find pre-coated with rhizobium.
Oh, interesting.
There's a big movement of planting the white, especially the dwarf white, as a lawn cover instead of grass.
I've done that.
Yeah,
I've got it out in my yard right now, and it's just
I'm
natural.
thinking about it for my front yard.
Yeah. My yard is natural, right? My neighbors see me twice a year out there. It's indigenous species.
My team's not there. I'm looking at your list. Like, can I say what my team would be?
Yeah, and would you join it?
I would go personally for sweet pea.
Sweet pea.
Yeah, like because they have the most beautiful little flowers. Oh, garden pea. There we go. Okay. And so it's like very close to that. And then you can just eat the pods straight off the plant. You don't have to cook them or prepare them in any way.
Oh, there you go. And so that's C. Maybe C will join us a little later today.
Yeah.
She's
I'm on there.
So the red clover seeds have arrived.
Oh, fantastic.
The lentils. So that's Steve. And then there's this adzuki thing. So that's you. That's
now,
Ted and Gil, right?
Yeah, I guess Gil's going to source his own in Japan.
He's going to have to source his own, but I'll get your package sent, and I'm expecting more of them over the next several days. So
now,
random question, just so I noticed the clover. Is the shamrock? I'm just really crazy here. I'm just going for the Irish connection. So
I'm gonna grab a cup of coffee. Keep on going, Liam.
Anyway, so
hi laddie.
Yeah, there you go. So anyway, I just like the idea of a fully clover
of shamrock, not fall off the face of the earth. You're doing
to be sure. Yes, especially on St. Patrick's Day, that we just all missed.
I believe shamrock's sorrel. It's not a clover.
Okay. There you go. Cool.
I've got a random funny story. A friend of mine, a friend of a friend, she came to me the other day. She's like, I need a botanist because I'm going to go for a world record attempt. I'm like, what? Tell me more. And turns out she got the world record for the most four-leaf clovers to be found in a given time period. And I was like, how did you do this? And she says, well, it turns out if you find one, there's usually a cluster nearby because it's a genetic mutation that can exist through the population. So she goes and she hunts for the locations for like whenever she moves to a new city. Eventually she finds where the four-leaf clovers are growing, and then she does another world record attempt.
Wow, there you go. That makes total sense.
But have you considered a land race? So in indigenous cultures in sub-Saharan Africa, the classic way like the women farmers tend to their fields is through what they call a land race. So there's the bean land races and there's like the sorghum millet type land races. So because the climate is so variable, rather than just planting one variety, one monoculture, like we do it traditionally in Western agriculture, but instead they will plant their collection of seeds. So they have many different types of bean that all grow and be planted in the same field at the same time. And so depending on which climatic situation occurs in that year, in that season, there will be a variety which thrives. So that way a family never goes hungry.
Yeah, that's a smart adaptation. Excuse me one moment.
Mm-hmm.
Well, that is fantastic. And so how might we apply that here? Would we, clearly we don't have the volume to run all of them at the same time, but we could run ground controls, or do we run simulations? Do we do something like, I just got my Cat 5 connector so my Wi-Fi doesn't stumble on my video. They just delivered it. How might you do that?
Well, the question would be, so each person is now growing their different varieties independently, maybe by their variety in its pot by itself or in its petri dish by itself, as I would do. But then you could imagine having more than one variety in the same pot or in the same petri dish, and then comparing the growth of a mixed community to individual ones.
Interesting. So what we might do then, instead of having Michael just had all these seeds come to him and he's going to distribute them to our PIs to begin growing them and sharing it, in our teachers that are joining us here on your next shopping trip in between staying at home. Maybe you can find the seeds that you'd like to there at the nursery if they're open, or at your grocery store. But maybe actually having us all grow collectively the half a dozen different plants is what you're suggesting.
Well, kind of, and this is very similar to the concept of in the Growing Beyond Earth project.
Mm-hmm.
So essentially, one of the things that one of the questions that the NASA Vegetables for Astronaut Health team had was, is it better to just grow one thing with the environment set up specifically for one type of bean or one type of lettuce? Or is there certain intercropping systems that are more efficient with plants that have complementary niches that help one another?
Right, the three sisters kind of thinking?
Exactly that, yep. And so that's what they've been doing. They've been testing different combinations of leafy greens in like the veggie environment. And so that concept of like positive community development is a new emerging area. It's really quite popular. The concept of agroecology has only become cool in the last like decade or so. And so one of the things that we could do, or the students should consider, is the relative benefits of having monocultures versus communities of different species growing together. I think it's a really interesting lesson and concept to explore.
Yeah, how might we implement something like that in our lab on station would be fascinating for me to think about. Actually, I guess we'd probably go to the magenta box to have that surface area. We could probably end up with maybe 5 or 6 max, but that could be done.
And it's one of those things you try in the classroom, try in the lab at home. You go, is there a way to get multiple seeds into the same container? And then you let the experiment evolve. Like, a lot of people think that scientists come up with a really well-structured experimental design at the beginning and then just make it work magically almost. But that's not the way. You come up with these broad ideas, you sow some seeds, you observe them, you watch them, and then you adjust and try again. And then sometimes from these preliminary trials, a real experimental design emerges that can be implemented.
Wait a minute, Richard. Richard, you got wait. So you're telling me that scientists don't start with a question and then form a hypothesis and then make their trial and it's one and done?
Well, kind of, yeah. That's exactly what I'm saying. I mean, we did have a hypothesis, and that initial hypothesis was really broad, i.e., maybe a community would be better than just the monoculture. But like, in order to answer that question effectively, it has to be broken down into a sequence of smaller experiments, so we can really fine tune and make sure we're asking a question which is more precise. So that way we can come up with an answer that's more precise. And eventually, if we do that enough times, we might be able to answer that bigger, broader question. But it's kind of building up to that with a sequence of smaller preliminary trials to see what is pragmatic, with the goal of sort of answering our perfect optimum question. But yeah, you're totally right. It's
it's a very different landscape than I think, definitely, than what the impression most kids come away with from school science. And I think this is a good place to start changing that, giving that general, everybody's working on the same broader experiment, but the little individual variation, as long as you're documenting everything, it can be incredibly illuminating.
That's what I get excited about.
Yeah.
You posit the broad idea and say, what would you like to do? In a way, teachers and students that are watching this live or seeing the recording of this, there is no right answer, no right way to do this. It's all about what triggers your curiosity. Why does, how does, where does, when does, what does, all those where, what, why, how, when questions trigger that. Let's go dig in and create some problems. Let's find out that it doesn't work. Let's try something different. Let's share with what we're finding. How embarrassing as it may be, I will share my embarrassing moments, and I will have some, as we try to make these things grow. But one of the challenges, Dr. Barker, are the low iterative rate that we have to deal with microgravity. Now, we seem to have been very fortunate, to, at least in the near term, being able to work through the requirements to get on station. But the International Space Station is being commercialized, and opportunities like ours, I think, will be more difficult in the future as people look to, wring the most profit they can out of each kilogram that goes up there. So how do we increase our iterative rate of design while staying terrestrial, if you will, to kind of help craft that hypothesis, right? And so I guess these ground trials with all this open-ended stuff gives us a leg up as we've got to begin planning, a leg up on our legumes. But at a certain point, you have to look and factor in this this gravity factor. So any thoughts on that, on how to kind of keep a high iterative rate? Is it a clinostat the answer, or?
Well, if you'd like to see the perfect clinostat for the example, go to cozycloud.com and you can see
about 3-axis.
Indeed, so the collaborative science environment has created a customizable 3D clinostat. They can have variable inputs put into the core, and we have pre-orders from all the NASA bases. But the jury is still out.
What does that thing run? How much does it cost?
$5K. Yeah. The competition in the market is from aerospace companies in Europe and Japan, and they were going at like $30K or so.
What's the size of this?
Big enough for Exolab to fit inside.
There you go.
Bigger than
we have I'll have to. It's at the office right now. Our single axis clinostat. It looks really funky, but it works. 1 revolution per minute, and it's across its axis like this, and so it just rotates.
And I think I mentioned that's how we got our first experiments into the space station, was through using 2D clinostats. So it's definitely the best entry level way to do it. And you could imagine all your classrooms looking at the different types of legumes that were discussed earlier, and measuring their presentation time. Is Steve on? So Steve's been looking at some work by Professor Purble, who was basically the gentleman that invented the use of measuring presentation time as a way to detect plant sensitivity to gravity. Essentially, you turn the plant on its side, you give it a gravitational stimulus for a period of time, and then you start rotating it in a 2D clinostat. The root tip will then bend depending on how much it remembered of the previous gravity vector, how much of a stimulus that you gave it. And so I had to do this hundreds and hundreds of times to build up the data set that we needed. An alternative, because I just had one 2D clinostat. an alternative mechanism for generating these valuable data that allow you to determine which legume is more or less sensitive to gravity. An alternative way to do it is to have lots of 2D clinostats in lots of classrooms, having lots of different people doing the experiment. Again, it's a dream I've been dreaming about for many years, but haven't had the infrastructure to do it. Hence, I'm here telling you about the idea.
Well, there you go. Well, I think we're building that infrastructure. And if we can keep it manageable with respect to cost, the concept is easy enough. We're looking at a motor and some brackets and maybe a different design.
And that's why the 3D clinostat that I mentioned isn't the right thing for this kind of situation. That's product designed specifically for NASA, which over the next few years will be tested in collaboration with, in coordination with spaceflight studies. And in about 5 years, we will determine whether it is a good analog for anything to do with spaceflight or not. I'm going to remain on the fence, to be honest. But we do know the 2D clinostat and the measurements of presentation time does work and has been used multiple times over the last decade. If anybody wants to do this, I have a research paper I've written on the area that describes the methodology, and I can provide that to you and anyone that would like that.
Do you want to stick the link for that in the chat box, Richard, please?
I'm gonna have to find it, aren't I? Okay.
Well, when you find it.
Hey, there's another opportunity here in that if there is a clinostat, whether it's a very sophisticated 3D or 2D or single axis clinostat, is for us to get a camera on it and just network it for everybody to look at. So if there is a lab somewhere, maybe yours or someone that you might know, that we can hook that up to it, we can just make it part of the experiment. Here's our candidate or a series of candidates. We're gonna put them in these in this clinostat environment. Maybe we'll just hook ours up and just run our single axis in the ExoLab because we've already got it configured for that and repurpose it. We originally had the Arabidopsis in there, and that would be good.
I'm looking for a video of a clinostat that my students engineered using little bits.
That was great. I really like that. And the first one, it was going around really fast, right? Then you lowered
they set a couple of different parameters, so I'm looking for it here.
I think the first one looked like it was spinning pretty quick.
Well, that was the thing, is they weren't sure. That was intentional. Was okay. Is it the speed? Is it the orientation? Is it the fact that it's spinning? So they had a slow spin, a fast spin, and they thought then spinning flat, like their controls, would be a control. So
it's interesting. I also saw, this is way back when we were first starting ExoLab conceptually, as I found someone that grew a plant on a record player. And they were spinning it at 33 RPMs, and they just let it go. Isn't that wild?
Yep, there's nothing wrong with that. It's fine. The record player is a valid piece of laboratory research equipment.
I'm sorry, there you go, right? Yeah,
so
I have one with a broken needle, so I can probably just set that up and just have it going at 33 or 45.
So I've definitely done that. The record player is definitely a very valid laboratory piece of hardware. There's nothing wrong with using that.
There you go. Just it's not a clinostat per se because it's doing something different. Your axis is different, right? Or is it what kind of effects we're seeing? It's really more of a
mechanical. So the key to making clinostat data really useful and it having more impact is the mechanical control. So you have the orientation, which is sideways, going around perpendicular to the gravity vector. And that gives you like the change in the gravity vector as the roots and shoots go over one another. But you also want the horizontal one, the one that's turning the plant so it's still maintaining a gravity vector, but it's providing the mechanical stimulus.
My clinostat on a record player.
Yeah. Exactly, yeah.
I have to deal with the power cord, but outside of that, solving that problem.
So we've actually gone through different permutations of 2D clinostat design. And we got to one it was great, it worked. And then we realized we couldn't turn it on its side. So and there's been, so that sideways control is always overlooked. You see it in a lot of the old papers and when you finish reading them, you're like, hang on a second, all the results they have here could just be associated with the mechanical stimulus of the motor turning. So the next generation of literature on the 2D clinostats and the data from plants in them is going to always have to require that new control.
See, teachers, sometimes your fourth graders are way ahead of the curve.
yeah, that video you played, right? I remember. That was good.
So are you looking for your video there?
I'm still looking.
There you go. So
it's here somewhere. I may have to change devices to do it, but yeah, that'd be faster.
All right, I'm going to go on repeat for our folks that have jumped in and just kind of talk about the International Space Station, the ExoLabs project, our challenge for you guys, for your students, and for you as educators. We have all different levels of students, pre-K, middle school, high school, university students have been interested in the work that we're doing. So every age is appropriate in terms of the amount of research that's required. More is exciting, but not required. What we really want to do is kind of be a port in the storm during difficult times where we can kind of convene, come together as community, build and share on ideas, try new and interesting things. And there's no really measured outcome. There's not a grade that we're going to be giving out. There's not going to be a winner. There will be a team that whatever lagoon we end up selecting that will fly, but I think we're all going to win. I talked about a mission patch. I want you guys to work with your students and design mission patches of what they might think about space. What we're doing with these plant experiments, in this case, this rhizobia bacteria and the lagoon, they have this really interesting relationship. They're exchanging carbon for nitrogen. It really allows us to have these crops, and the benefit ends up being essentially a green fertilizer without artificial fertilizers being needed. Great for our thinking about the future as we want to put a settlement on the moon or on Mars. I don't like to call them colonies. I think it's kind of has a bad connotation if I think about the past.
Imperialistic.
Yeah, so it's definitely settlements.
As a Brit, there's a different connotation for colonies.
So tell me, I mean, from your perspective, because I'm pure, born and raised in Oakland, California. Represent. What what does that mean when you hear colony?
How to put it? Britain did really benefit a lot from the colonial era. There are many, everything in life has many pros and cons to it, right? Mm-hmm. You can look back at history and you can look back and just see the positives, and you can look back and you can just see the negatives. Mm-hmm. The reality of the people that went through it is somewhere in the middle, mm-hmm. for most people. And I'm not saying that the colonies of old did more good than bad. I'm not going to go so far as to say that. I'm not a historian. It's not my place. But I do know that the older generations in the UK definitely have fond memories of the colonial era and the benefits that it brought to European society.
Oh my goodness, English as a common tongue for the world. Mm-hmm. Essentially, as a scientist, if you're going to travel anywhere, whether you're, whatever language you're speaking, and that's my laziness. I can go anywhere and pretty much look for a young person. Do you speak English? And they do, and I can find my way around that town, around that city. And so, if anything, that colonialism did enable, I think,
increased connectivity around the world. So we just have to make sure that the next wave of colonialism doesn't have profit as its driving force. When you have profit as the sole and only driving force, it inevitably leads to the community making decisions that are not for the benefit of the people, particularly the local people. And that has led to a lot of atrocities. So this is why just modern free markets are kind of worrying, because there's no conscience to modern economics. We need to have a shift and away from the old-fashioned formula of corporations and create benefit corporations, companies that they have a bottom line, but they also have a mission. And I think SpaceX is one of the prime examples of this. Space Exploration Technologies is a company, it is a corporation, but they have a goal, and that goal will have a benefit for all of humanity, which is the formation of a permanent colony on Mars. And so as long as that colony doesn't then have profit becoming its next driving force, then that colony can do tremendous things for humanity's future.
I think that's autonomy for that economy. And I think that's unlikely because of the infrastructure cost, but that's just me maybe being a middle-aged negative guy.
I think that's really likely. And there's a great book called Red Mars. It's part of a series, Red Mars, Blue Mars, Green Mars. I recommend reading it. Maybe in 300 years from now, we'll look back at it and it'll be the next Bible as it predicted the next wave of humanity's presence in space. But it delves into all of those interesting things, not just the scientific challenges, but like some of the political ones. And it really makes you reflect on humanity's past and how there's been echoes and patterns for humanity's past, and how if we don't learn from that, those echoes will repeat in humanity's future as we go out into the stars. So as a scientist, I try to avoid economics, I try to avoid politics because I feel like helpless that I can't change them.
Right.
But as a scientist, I can produce data and I can educate people and arm the next generation with the inquisitive nature that they need to look at the past and imagine a new future without some of the flaws that did happen in our past during colonialism. So maybe we'll have a greener revolution in the future.
Yeah, I think we got to avoid the Borgian way too. We will assimilate your uniqueness into our own.
Mm-hmm.
Right, there we go. Yeah,
so the paper, I just shared the link to the paper I mentioned about us using 2D kinestats to assess a presentation time. Mm-hmm. Problem is, I've just found out it's behind a paywall. I'm so sorry, it's behind a Springer Link paywall. So I will be downloading the PDF and getting that to you so you can distribute it with people who are, because there shouldn't be a paywall. Oh, look at that. That's awesome.
So this was designed by a couple of fourth grade girls last year. And I think those, oh yes, those do have your I'm not sure. Those are either Arabidopsis or Brassicarapa. I can't remember which.
Oh, I love it.
So you can see here, they've got rheostats that controlled the rotational speed. And then they've got their horizontal axis and their vertical axis for the motor, the rotor of the motor. And they've just hot glued the Petri dishes to the, it's an adapter that you can get, that comes with the Little Bits motors now, that you can use Legos and Connects pieces to attach to it. So we just made a mounting stub and glued that onto our Petri dishes, taped them shut and let them spin. And there's just an absolutely gorgeous photo.
I love it.
Pull that up.
That's great.
Share.
So yeah, there's engineering challenges with this as well, for sure. This format here, essentially a week ago, we decided we wanted to do this because schools are going to get shut down, and this is really organic. We're coming together. Dr. Barker's joined us coming out of the blue. So glad you could join us back to back. And I welcome you to join us any other times during the next 30 days or so. But we want to hear from you as teachers as well. It's very informal. There isn't a rigid protocol here as far as going through what the rules or obligations are. We want to hear from you and help craft kind of pedagogically the way you think about your class, the new dynamics that you have, how you might be outreaching to your students. Your students may not have internet access at home. They may not have a computer. They may. And so we want to understand what restrictions or what advantages that you have at your disposal so we can best use those in this investigation. We want to have fun and we want to build community. So we welcome you to come in with your ideas, and it's okay if you think you're coming in from left field. We want to hear about it. Bring it in, share it with us, these new and novel ideas. And my apologies in YouTube that when I set this up, jumping over from Facebook this morning, the comments are turned off, and I think I have to kill the whole feed and figure out how to change our configuration to make that live again. But 2 o'clock today to 5 o'clock Pacific time, we're going to run this again. If Facebook's working, we'll be there on our page, Magnitude.io's page on Facebook. And if we're still having difficulties connecting, then we'll be back here on YouTube. It's probably going to be a different URL, but we'll send that, and that'll appear on our Facebook page. And then hopefully comments can be added. So,
say, Ted,
yeah.
So just quickly, I don't know if comments or chat is different, but the chat is working on YouTube.
Oh, great. So Tony got it working. Fantastic. Because it was not working for the first 2 hours. He sent me a note, but now it is. So great. Do we have comments coming in then? I haven't.
It's just us.
No, it says comments are turned off. Maybe I'll refresh.
Yeah, so it may be a different distinction, but if on mine
within YouTube, right now it's just Liam and me, so in there.
Okay.
Yeah, to the right side of the video playing, at least
good.
on mine,
Okay, so
I can see.
Tony got it. Tony, thank you. That's good. I was really worried about that I had to stop everything and start again, so I just let it roll. That's the thing about getting these things figured out. And also topics of interest. If you are doing your own work in your classroom and you feel it's relevant to ours, talk to us. Team at Magnitude.io gets to an entire team. That's our folks working on the stack. It's front end, back end, business development. It's everybody. And let's bring you into the conversation. Share your knowledge, share your experience, best practices, frustrations. If you've done something in the past and you want to make sure we don't run into the same thing, your knowledge and experience is going to help us collectively as a community do something fun and cool. So we definitely don't have the answers. I know I don't. My background's an art guy, and I'm privileged to be working with super smart people. And everyone here in this chat, definitely, I have to look up to and respect for their knowledge and experience, whether it's an educator, whether it's a researcher, whether it's that young man right there that's going to teach us something new about the world. We welcome you and we invite you to join us in the conversation. I don't just want to be talking head up here. And we're really privileged to have us join with Michael and Lauren and Dr. Barker. So definitely keep the conversation going here. Maybe we'll loop back to the top here, Michael, and talk a little about the plant you've got in front of you.
Yeah.
Maybe loop back to experiment that we just got bagged up as we get ready to send back home, and help us kind of tie into where are we coming from. If someone just logged in right now and they feel like their feet aren't on the ground, they're floating around a little bit, how can we kind of create a direction of what we're trying to do?
Right. So we've got this problem that we're trying to solve, and that is how can we live sustainably off of this planet? I mean, it's hard enough to figure out how we're going to live sustainably on this planet right now, to be perfectly honest, but people are trying. But humans are innately explorers. And if we're going to explore any further than low Earth orbit, we've got to have a way of taking food that is palatable, that is nutritious, and that's not going to be protein bars for a 3-year mission. And so we're going to have to grow some of the food that we want to consume along the way. It's also there's just no way we can pack enough food for that long of a mission. Even shelf lives of things start to go bad. So you've got to have a way of having something that's fresh too. And so the where this started was, okay, we want good quality food. Plants are a good place to start in terms of energy and everything else. But there's a problem around, well, the plant has to be fed. It needs nutrients beyond just the light. The light's the easy part. The plant will produce plenty of sugars, but if there aren't enough of in particular, nitrogen compounds that it needs, it's not going to be able to function in terms of photosynthesis. It's not going to be able to assemble the amino acids that are necessary. So it's just going to be fiber at best, and probably not very tasty. So being an Iowa farm boy by heritage, I immediately thought about legumes. And as any good farm boy knows, legumes have a special relationship to the soil, or a bacteria that lives in the soil. And they form a symbiosis with this bacteria called rhizobium. There's also another one, azotobacter, but we're focusing on rhizobium. But frankly, I find it a more interesting and more compelling relationship. So if you're not aware, symbiosis means both parties get something out of the deal. Ted breaks it down and simplifies it. It's like a barter system. I got something you want, you got something I want. Let's make a deal. And that's kind of what, through evolution, these plants and microorganisms have done. So we all swim through a sea of nitrogen on the space station. It's essentially the same atmosphere. It's mostly nitrogen. So there's plenty of nitrogen available, but it's inert. It can't react with anything. N2's bound up tight. And it takes a tremendous amount of energy to break those bonds. A lightning strike can do it. A tremendous amount of energy from fossil fuels can do it. But plants and these bacteria do it as part of their life cycle. So the rhizobium, the microorganisms, those bacteria can take the nitrogen and convert it to ammonia and then into nitrates and nitrites that the plant's able to metabolize for its own production, and then also assembles all of the building blocks of the rest of life itself. So, ultimately, we're all indebted to these little microscopic organisms, rhizobium. In the root system of the legumes is where all this happens. And later today, I'm hoping this is a mature plant. You can see that it's flowering. It's also produced a couple of pods. So it's doing well. This plant is about a month or so old, no more than 6 weeks. It originally started in a test tube like we use inside the ExoLab. So one of these test tubes in some nitrogen-free media. The roots were inoculated with the rhizobium so that they would start to nodulate, and then transplanted into just some potting media. This is a empty water bottle that cut it in half. The bottom part of it becomes a reservoir for water. The top part of it is the plant. The cap's on there. There's a piece of cotton string that extends up into the potting media to just wick the water up. I need to add some water here because this is empty now, but also I'm going to uproot this today. So I want it to be a little bit drier, and we'll see if we can find some nodules, and then I'll replant this because I don't want to lose this plant, but I'll harvest a piece of root material, and then we'll also do some dissection. We'll share that later today in the program, and you can extract that as a clip and share that with your students if you like, or better yet, have them do it themselves. So I'm just kind of riffing here. I think, did I cover everything, or you're muted, Ted?
Yeah, I did. So this is great. That's our focus for 2 o'clock today, Pacific time. We'll be back on, I think we got the YouTube going here, and we can get it on Facebook as well. So I think that's going to be our broadcast method this afternoon, 5 o'clock Eastern, 2 o'clock Pacific. Michael Wilkinson will take us through, I guess, a dissection of that plant. So we kind of take it apart, but we also will back up and think about why we got there in the first place and what our challenge might be looking at these various legumes. And we got to pick one for our flight. What I'd also like us to do, I don't know if you have an empty water bottle there, but take us through that real simple step, or if we even have a PDF or something else we can link in the chat. We can share, put that maybe on the
I've got
YouTube
one. We'll
channel.
construct it. We'll go through the whole thing.
There you go.
There, Lauren's got one.
Lauren's got one running. So I don't really try not to use the water bottles anymore, but I'm going to try to see if I can't dig around and find something.
Richard knows my friend from his institution, the dumpster diver king himself.
Yeah. So that design comes from NASA essentially, right?
Yep.
So there's this wonderful gentleman, Paul Williams. He's a
Paul
legend.
Williams, the king of Arabidopsis. Oh, not Arabidopsis. Excuse me, Brassicarapa.
In general, the cabbage king.
The cabbage king. That's right.
That sounds pretty good.
He is a beautiful man, and this is where really he changed the way I thought about laboratory science with students. If you can't make the apparatus yourself, you're not doing science. And it's like dumpster dive. He used to, I don't know if he's getting up there in years, so I don't know if he still bicycles everywhere, but he had a basket. I think it wasn't it like a recycled or reclaimed milk case? Those, they back in the day, you'd get your milk bottles in.
Right.
And he would literally pass by dumpsters and find anything he thought he could recycle and repurpose.
There you go.
And he made all of his own lab equipment. It was great.
Well, recycling really went through yesterday, so do that. All our cans are empty if I went up the street. I'm going to have to go a few blocks over where they're going to be picked up on Saturday maybe and see, what are you doing in there?
Yeah. And the great thing is that this is the piece that I do with my students. Like, okay, you realize it's a myth that this plastic is actually being recycled. It doesn't happen anymore because there's no practical way to do it. So this stuff's just ending up in landfills in other states and other countries. So the real
no longer out of the countries, they're sending it back now.
Yeah, now they're sending it back.
Yeah.
Let's reuse it. Let's find new ways to do it. Let's not produce more plastic. Let's utilize what we've already done.
A great math exercise is for the students to calculate the cost of their water coming out of the tap.
Yep.
And the cost of the water coming out of the bottle. and look at the the magnitude difference in cost. And I think they all want to start.
What you're paying for a bottle of water, you'd have a fit.
Yeah. And so this takes us back to the wonderful documentary, The Garbage Warrior. It's on YouTube. And
that one.
It's great. There's this wonderful architect in, I think, the New Mexico deserts who fought for many years to be able to build homes out of like bottles and cans and other like materials. And he's shown an alternative way of building homes that are ecosystems that like recycle your waste and brown water and produce food and the things that you need to live. It's a really wonderful show. Garbage Warrior, I strongly recommend it. It talks about building earthships, not homes. And so this wonderful thing that Paul did by inventing this really simple mechanism for to allow teachers to grow plants easily and cheaply with their students was kind of very pioneering. It was before this recent wave of like recycling and the green movement. And so he was really before his time in that respect, in those regards. And so it's just really great to see how we can then take that to the next level and work with those foundations that he produced.
And you know, when we're off world, that's exactly what we're going to need to do, right? You won't have all that stuff around you.
And interestingly,
to repurpose your vehicle.
he then, so as he was doing this, because he wanted to bring vegetables into the classroom as the cabbage professor of UW-Madison, and he designed a fast breeding version of brassica. It's now called the Wisconsin fast plants.
Oh, okay. That's the connection.
Exactly that. And this is how he got it into outer space. So the Ukrainian Space Agency wanted to collaborate with NASA just after the fall of the Iron Curtain. And his plants were, the Wisconsin fast plants went up. And so this then developed and grew further and became a large, eventually an NSF program, the Wisconsin fast plant program. And he eventually got that deal because he was at an NSF board meeting sitting there, and he says himself that he got bored at the board meeting. So he got his fast plant out of his bag that he was carrying around in those exact plastic bottles. And then he started pollinating them in the meeting. And then everyone
with a bee thorax glued to a toothpick.
Literally. And then people in the room went, "Ooh, can I have a go?" And they passed it around, and all these old professors enjoyed like doing this plant crossing that he was doing as part of this breeding.
Wonderful.
So again, it's one of those serendipitous moments.
It's that infectious passion that people have when they really love a subject, where they just get immersed in it, and they really don't give a whim about what someone cares about, their response to their excitement. They're just going to do it. And that's the more people I can surround myself that are like that, the better the world will be, I'll tell you. Whatever your interest is, skateboarding, it doesn't matter. It's like whatever, planting.
Oh, don't get me started on skateboarding.
Oh, no. I'm a horrible skateboarder, so I don't know. That just popped in my head for some reason, but.
I've got the scars to prove that I was all right once.
All right. Yeah, no scars, no proof, right? Yeah.
Well, you weren't pushing yourself hard enough. One of the two.
There you go. Now, so
Richard, I think what you need is we need a GoPro tour down the hill to the lake on your skateboard.
Ooh, that's dangerous. So UW-Madison has this really big lake and a really big hill. And so the skateboarders always have this like dare game when they do their best to fly down there in one go. I was able to do it in 3, which I've been told I'm not allowed to try again by my partner.
It's probably smart. Just by the description. I'm going to kind of bring that back into what we're doing with plants if I can. So when we disrupt a plant, when we
science.
No, it's fun. I like it, but I know the folks are watching and they're trying to get something. I hope folks are tuning in. But when we stress a plant out, you showed this amazing video yesterday under inflorescence, and you could see when you cut off a leaf how it responded to that. And now we're giving it, so we're going to throw it in a microgravity environment and confuse the heck out of it. And so these responses that living organisms have with the world around them is really, it's absolutely amazing. And I think if I could distill the work that you're doing and others, when they think about genomics and epigenetics, it's this interaction we have with the world around us. That if I was raised in a different part of the world or a different time, that my physiology would probably be different. I mean, there's some fundamental building blocks that would be the same, right? because of who I inherited my genes from, but my environment would literally kind of be affecting my outcome as I got older. Is this true? I mean, is this fundamentally correct? And I guess epigenetics is, at what point does that become something that I pass along to my offspring, right? And so if I was living in a very polluted environment and I had offspring, would that be different if I was living in this really beautiful environment and my, same genetics, everything else? Would they now be suffering from some kind of ailment, or would they have some miraculously new sequence that enabled them to do something else?
Yeah, there's a really interesting case study from, I think it was Canada. So there was a traumatic event. I can't remember if it was World War II, but essentially they're able to detect changes in the next generation, like the wives that had like husbands that died in the war and that kind of thing. They're able to detect a footprints in their epigenome of like the stress that their parents went through. There's a few different studies in this kind of area. And so moving forward, as we go out into outer space and we send life to these extraterrestrial environments, they're environments that life's never encountered before. And so generally if you haven't encountered something, it's pretty stressful, right? Like the American tax system. Oh. So when we go into outer space, we're actually starting to see some of the changes that's happening in the epigenome of plants that have been grown in orbit. There's a wonderful study that's been done by the Chinese Space Agency, where they had a deep flying space satellite that took Arabidopsis cell cultures on that voyage. And so now we have a list of locations on the genome where methylation occurs. So methylation is one of the epigenetic modifications that can happen to DNA that causes swathes of the genome to be switched on or switched off. We know from the area where the Chernobyl nuclear disaster took place that plants were able to withstand the increased radiation. But as a result of that, when we look at their genomes, we see an increased quantity of methylation occurring. Those early studies didn't look at the location of methylation, but that's what we're now really excited about as we look forward into the next era of biological research, as we look at these plants going out into space and we identify the regions of the genome that get these epigenetic modifications. So that will help us understand how the plants will try and evolve to adapt to these new environmental stresses and new environmental stimuli.
Mm-hmm. This makes me think of tomatosphere, and the question that I've had is the embryo in the seed? Do we have studies really to see if that is affected directly, or do we need to have the plant go through sexual reproduction for those kinds of genetics pieces to be passed on?
Well, I think the way you question that is, do we need to have our natural selection working on it post-modification? So by looking at the location just from the first generation being up there and saying, hey, this is the spot where we're seeing the epigenome change, that's interesting. But the next question is, will that actually then confer advantage that will cause evolutionary pressures to select for that variety? It's hard to do that with Arabidopsis, but there are researchers at the NASA Ames Research Institute that are doing those types of studies with Drosophila, the model fly, because you can rear thousands of them in a small space. So yeah, to looking at the evolutionary side and multi-generational studies, it pains me to say, but we do have to look to the Drosophila model to see how that will go in outer space, because plants, it's just the simple numbers that you need is hard. Yeah. And then the other problem is then
there might be an opportunity there with what's the gentleman's name? He's the hotel magnate. He's got his
Bigelow.
Yeah, right. He's got the expandable modules, and they have a small scale version of that. And all they did is they just pressurized it to make sure it worked. Yeah. I was thinking that would be the absolutely amazing greenhouse, right? Where you just populate it with plants, and you just it was your greenhouse. And you go through, and because they're just checking pressure, and if it, sad for the plants, but if it didn't work, it collapsed or what have you, no one would be harmed. Your experiments would be ruined. But there's a space that right now is just a test. And how is it being used right now, right? So to me, those kind of opportunities, and of course, being sent up, it's very compressed, it's very small. and you append it to the ISS or to the gateway or what have you. And then NanoRacks just put up the new their new what you call it airlock, right? So they have their own commercial airlock now.
Yeah.
And those things are starting to happen, and being able to plug in kind of like Legos, where you build your greenhouse essentially. So it's not just about your plant research. It's literally saying we're architecting a greenhouse to plug into the deep gateway or into the ISS. And it's separate from all the other things that you're doing. And it's built just for this. Then you have your rows and rows of plants, all whatever it is, Arabidopsis or who have you. And then maybe you can do it. You know, what is it? How much does that cost? 40 or 50 million? I don't know. 500 million? No, not that much. But I think if we get the right folks involved, why not try to pursue something like that and say, hey, can I get access to an airlock? Because
we've got Axiom coming on too to do the commercial modules that they want to expand the station. So
and Tango has something called ST42. I don't know if you guys have heard about this prototype. So Tango, Space Tango is the company that we use to get up in orbits like NanoRacks. We got to know them right when they spun off from Kentucky Space Grant Consortium as a commercial enterprise. And Twyman Clements is an amazing guy. Have you worked with him, Dr. Barker?
Nope, can't say I have.
So TechShot, I think, has collaborated with Twyman on a couple different, and they know each other pretty well. And I've talked to a few folks over at TechShot and like to learn more about what you guys are doing. But fundamentally, I think we can kind of explore that. But ST42 is a proposal. It's basically a factory in space. It's a capsule. Imagine like a Cygnus or something like that, or Dragon. It's launched, it goes into orbit for a couple weeks, and it comes home again and doesn't connect to the station or anything. And all they're doing is production in microgravity. In this case, it might be pharmaceutical or material sciences, like fiber optic cable. They're now running fiber optics because the occlusion rate is far lower. It's very clear as you're making this cable. And so your distances, without having to rely on repeaters, becomes higher. And they're thinking economically, it's okay to send the raw materials up, produce fiber optic cable that's pure, send it back home again, kind of like crystal studies or something like that. And so the idea of ST42 is to go up into orbit, do your manufacturing or doing your research or whatever, and just come home again. It's the entire capsule. And so that's a prototype. They pitched that, I think, almost 2 years ago. And I think they're trying to raise funds around it as they do their more commercial enterprises with brain organoids. And I think they ended up going Budweiser, and they did some yeast with Budweiser, stuff like that. And getting these brands up there. Nike, I think, is doing some stuff with National Lab now too. So the brands are showing up. Can we do something meaningful?
My favorite one is Aeros. Do you know the Aero bar? So it's a chocolate bar from the UK, which has loads of bubbles in it. Yeah. And as you look from the top to the bottom, you see the size distribution, the bubbles get bigger. And that's because of gravity. And so they wanted to know if they had equal bubble distribution throughout the chocolate, would it increase the flavor perception? And so they were able to make some chocolate in microgravity by injecting the air into the chocolate. And then I guess somebody had to do the taste test, right? Did it taste better?
Someone had.
Must have been the most expensive chocolate ever eaten. And I bet there was no difference too.
Oh, there you go. Well, you think about like space beer, right? Or whatever. So I think there's some interesting commercial applications if someone can grow something or develop something that's used in the process of food, in which it is kind of exclusive, right?
I personally believe it's just going to come down to branding. Just like when the Chinese flew the wheat seeds, and then they found some wheat mutants, albino mutants, that were created as a result of cosmic rays going through them. You can do that with mutagenesis on Earth using conventional breeding techniques. It was mainly just because they wanted space wheat as a branding thing. I hear
space wheat.
Well, that I hear is being done as well, right? I think the Budweiser is the same kind of formula. But I'm really excited by crystal growth in outer space. It's a huge area. There's a lot of drugs that have been invented thanks to researchers on Earth growing crystals and using those protein crystals, and then using those protein crystals to design drugs to cure certain ailments. And there's certain protein crystals you just can't grow with gravity. I don't understand why. It's a combination of physics and medicine that's beyond my pay grade. And they were able to then grow those crystals in microgravity and then design drugs with that. So it's definitely a very exciting future area of research from the commercial perspective.
Yeah, speaking of crystals, help me understand what's happening with these plants here. Well, it's interesting because I'm not quite sure what this
That's one
is.
that's got the stuff on the stem.
Yeah. Do you know what that is? You
Um,
probably can't see it here,
How
but
do you see with that? Usually, like, is it hairs? So
no,
most
it looks like it's
It looks like salt crystals
shooting
almost.
like salt or crystals or something, and it's formulating around the body. I might take a picture and send it to you.
I'd love to see it up close. Yeah.
Yeah. And yeah, it's curious that it doesn't happen on all plants that we've
One
grown.
of April's plants. Who's no? One of the partners has one too that's got a lot of it, and the photo's really clean.
Oh, there you go. You know what we didn't do? My goodness, we spent all this time talking. We didn't actually show the platform at all. Caught up, and let me do that. Log in and just show our educators here. We're already, geez, we spent all this time, and we've got about 30 minutes left in this session. But do join us this afternoon, guys. 2 o'clock Pacific, 5 o'clock Eastern. We're going to run till about 5 o'clock today. I'm not sure about our calendar next week, but I want to have several of these next week as well. I'm hoping for additional guests. Dr. Barker is always welcome to join us all and every time. This is fascinating. It's like I'm getting a college education here for free.
That's the goal.
Just don't send me a bill, huh?
Oh, Lord, no. But Chris, I also mentioned my friend from Kennedy Space Center. You need to reply to her because she would have to get authorization to show any of her slides from NASA. So whenever she does public engagement, she has to notify the people up the chain. So she's happy to get on board. And yeah. Beautiful.
Yeah, I think I sent her a quick note. It was this morning. Maybe I didn't. I'm not sure. I'll have to look again. But I have every intention to reach out to her. And thank you for that introduction. So what I'm doing here is logging in. I should probably log in as a teacher rather than as a root admin. So give me a second. Oh, let's try Maggie. All right, so I'm going to share my screen. And hopefully you guys can see that. Yes. This is your classroom environment that, oh, this is interesting. We modified it. I haven't been on since I saw it on our main screen, but this is now the Leguminaut challenges plugged right in there. So maybe I just click, I won't go there because I'll get confused about some new things, but under our classes here, you might have a number of classes that have different programs, and you can kind of select your class, and in your class, you assign lessons. The lessons, again, are built around the next generation science standards, these cross-cutting concepts that you can use across all domains of science, like the scientific method, disciplinary core ideas, which you'd expect to find in your lab books, in your textbooks, and then the science and engineering practice kind of being integrated, SEPs, science and engineering. And then you have your ExoLab experiment running again. This is day 15 on this experiment. And hopefully this is going to connect to a live experiment. See what happens here. Yeah, here we go. And so here we are, day 15. So this was back on March 19th. It was yesterday, I guess. I don't know why it's not giving us today, but here it was back in March 3rd on the space station. But what we're able to show is the plant growth in that particular time. We can see here is the UTC time of this image. There's a current temperature of that plant, humidity, and CO2 in parts per million, and micromoles per square meter per second is the light level readings. And then the same thing on in space. We've got, let me move a little wider here. Temperature just about the same. It's really too toasty, wouldn't you agree? We really got to get it down 5 or 6 C. It's drying out 25 degrees. And this light level reading, I think, is incorrect. I've got to talk to our team about that. Apparently what's happening is we're seeing the light level when it's off as opposed to on, giving that reading. But what we also have here is a slider on the top, and this is close to what you want, Dr. Barker, but what we want to do is I've asked our team to get all the images and then create a little time lapse for you, unless you'd rather just have the raw images.
A folder would be lovely.
Yeah, but what they've done here is they've all given them the same name in each folder, and then you open it up, and it's weird the way we're getting the day. We need to tighten it up. But I can take this slider and I can go back in time. And here's day 12. I can slide it back again, and we can see this is day 10. Oh, come back later. Come back here. There we go. Here's the plant on day 9.
This is
So on the ground unit, the experimental is on the left, control on the right, and then on station, the experimentals are on the outboard sides, and the central one is the control.
This dark spot right here is a screw, by the way.
And a group of students like, there's a spot. They zoomed in and finally figured out, oh, it's just a screw.
Yeah, it's this is a 3D printed case, of course. I wonder about outgassing, what have you, but I guess that's a further discussion. But we can go back even further. Will this kind of information be helpful for you, Doctor?
Yeah, it's really cool.
Okay.
Just like, there's been so many experiments that have been done that have no imaging. And for someone who's a plant physiologist, someone who appreciates like the size and shape of plants, like this is it's beautiful.
Yeah. Now the image you're seeing, I just turned it off because I'm gonna turn it on again, share my entire desktop because I'm gonna zoom in on these plants. What we can do also, if you select an image, you get a boom, super big size, and you can kind of see much little better detail there.
You know, so you have a fisheye lens, is that right?
That's correct.
And because there's like software in a script in MATLAB that can convolute or decurve the fisheye.
Well, let's run it.
Because yeah, exactly. That's just something. Because when we do photography of plants and try and measure them, we want the plants to the left and the right of the center to be comparable to those in the center. But if you have a fisheye lens, it distorts the images around the edges.
It definitely does. Our tubes are curved.
And that makes total sense. Don't get me wrong. When you're up really close, it makes sense. It's the right thing to do, have that. But but that's the great thing about computer technology, computer science. We can then like use code to correct for that, so that we can still extract the correct biological data from the images. There's a lot that you can measure there.
Right. Now, other things that we can do that can be helpful for you is on the research end and also for our students. Like we have a scale that you see on our lab, but we really don't have a scale here on station. Now, just as a marker to know that it's 5 centimeters or 2 centimeters. I mean, you can kind of guess it's a 38 millimeter tube. It's 200 millimeters tall, so you can start extrapolating.
So it's the same tubes?
No, they're small. They're 28 by 35, 135s on station.
Yeah.
Because you just need one feature to kind of normalize it to. When we've used Petri,
so we know they're basically 1 inch in diameter on station. So 2.5.
Now we have flown the Petri dishes, and so we have different configurations. We flew on our bacteria experiment with 35 millimeter round plates, and the more standard Petri dish, that kind of square one with the grids on it. When we flew Arabidopsis, we flew it that way. We also flew it in the magenta box. With kind of looking down, and that was our first experiment, and that gave us about 5 days of worthwhile growth before we watched them just shrivel up and die.
Cool. Again, I'd love to see that.
So we're kind of hit and miss. We're kind of figuring out where we can go, but with your guidance, we can pretty much ensure that our future mission as early as Flight 8 follows maybe a little tighter protocol and emphasis on engineering that optimizes the results that can be used beyond basic educational practice and basic research, but into the deep science that you would like to investigate, the meta versus the micro, as you kind of need something, you're asking for something at the larger level, the macro level.
Yeah, because my job with NASA GNAB is meta-analysis, is trying to collect together as many different studies as possible and then look for like correlations and between them. Sometimes when you look at an experiment by itself, you can sometimes you don't learn anything. Sometimes you do. Usually you do. But then sometimes when you then look at these things from a bigger, broader perspective across multiple experiments, then suddenly subtle patterns that were prevalent become clearly more important. And particularly when you start to look at all the different types of hardware. Would you like to see some of the different types of hardware that NASA used to fly plants?
Absolutely.
Because I have to go in about 15 minutes, but I can just show you a few really cool pieces of hardware if you let me share.
Yeah. I think I've unshared now, so go right ahead.
Okay, cool. So if I share that. Okay, cool. So where's the full screen button? There it is, that one. Okay. Oh, no, this is in the way. 2 seconds. Okay, so veteran of multiple spaceflight studies, yay. And so we get cool mission patches. So remember, if the kids are still listening, blast off. You've got to come up with a good acronym, and it's got to mean something. It's probably the most important thing for all NASA spaceflight studies. So we work in Astro Body Lab, and we investigate how plants respond to stress. So we've been using different custom hardwares to put plants into outer space. This is the space zucchini. I'm not sure you can see my mouse on the left. Yep. You can see it's a early piece of custom plant growth hardware invented by Tom Pettit. He wanted
zucchini tweeted on its mission.
Exactly that. It has like some poetry that it wrote. You can see it's custom because it's got this tape. This is Kapton tape. It's a flight approved tape. Everything has to be flight approved. And you can see the roots growing and the shoots growing. So I actually really love this because you can see the roots and shoots. And
it's beautiful. It's floating around. That's even the best thing right there.
Right. Yeah. Next to it here. So this is an early study done from the ABERS hardware. This was done by Robert and Annalisa Poole. This hardware was essentially used once before it broke. Cosmic rays break computers if there's not redundancy in the computational system, they don't last long. So most hardware on the space station has 3 computers. So if one of them gets lost to a cosmic ray, the others take over until the first one gets repaired. And what you can see here is the shoots. We have the hypocotyl and the cotyledons and the first true leaves stretching up towards a light rack, which is just out of view here. You couldn't see on the photography. And then we have our roots growing down. Usually you're down towards the gravity vector, but here in this instance, we're actually seeing them go down away from the light vector. And one of the things, if you look really carefully, you can see the camera in the background just there. There's the little lens. Yep. So this was a really awesome piece of hardware, and they did some really beautiful work with it. Problem is, it was completely unique and has never been used since. So since then, we've started looking at other pieces of hardware, and I'd just like to introduce them. This is the brick. This is the workhorse of NASA. You don't get lights, you don't get camera, you just get 6 samples. One of those samples gets replaced with a hobo data logger, monitoring the temperature and light in the box as a whole, but that's it. So you get 5 samples.
And the schematic on that, I'd be very interested in understanding what the schematic is and any engineering drawing.
Schematic is that. Sorry. Savannah, leave it. Sorry, there's a post person here.
That's okay.
Savannah, come here, go. Oh, you're a good girl. Yes, you are. Okay.
It's
so we have the
life.
And I must say I'm a big fan of the brick, but it's a very simple tool, and so it allows very simple experimental design. And I mentioned there's no cameras, so this presents a huge opportunity because we have a lot of genetic data that's come from that with no physiology to correlate with.
And dimensions, can you give me an idea of those dimensions? They're larger than our 2U.
This little Petri dish fixation unit, PDFU, has a circle here. This is where the Petri dish gets inserted. And that is that small Petri dish that you guys use, the 60.
These are very small.
60 millimeter one. Yeah. Savannah, leave it. Come here. Oh, you're a good girl. Stay here.
About what, 10 by 10 by 3, maybe 4.
Wow.
Yeah.
Hold on a minute. So you're telling me I can make 10 of those bricks in here?
No, but you could probably fit some of the PDFUs, these things here, in there. But the brick itself is bigger than that.
Right. Well, I guess what I'm saying is we would re-engineer that, but conceptually, there's some redundancies you've got going in there with each of those bricks. You've got your primary experiment, right?
And
it's
so,
really
so we get our biological replication this way by having multiple Petri dishes. Each one becomes a different biological rep with multiple plants inside that become the technical reps.
So imagine if we changed our format here and this was all just dishes. I get 10 dishes in here, but I need proper lighting and I need proper imaging.
Well, you don't need proper lighting because they didn't have any lighting at all. So they chose a different thing, which was fixation. The cool thing about the fixation system, so there's multiple levels of containment. You've got to have like.
Oh, that's what I want to see. There we go.
Because that's what is important for NASA. You can't let your chemicals out. And then there's this location here on the side where the astronaut can inject a actuator, basically a glorified syringe that injects into it the RNA later. So essentially you could imagine in your Magnify system automating that, where you have a fixation system like that's, but that would always be at the expense of the photography. And so my suggestion would be using the data that's already come from the bricks and using the same Petri dish and then imaging those and then marrying that physiology data with the genetic data before trying to reverse engineer the brick into the exolab, because the exolab has the wonderful characteristics all of its own, right? So why go back in time to the brick when you can use exolab to provide insights as to what was already done in the bricks. The veggie is my favorite piece of hardware. It's so simple: lights, plants, and we'll come back to that in a moment. It's got everything you need. Then there's finally the advanced plant habitat. I'm not sure if you're familiar. This and the veggie are both made by Sierra Nevada Corp. They have an office here in Madison, Wisconsin, from when they brought out Orbitech. Orbitech was essentially a company that invented the concept of using LEDs for plant growth indoors, and then started applying it in outer space. And so the advanced plant habitat is huge. It's big, it's noisy, it's got loads of bells and whistles, and thus the more complicated you make something, the more likely it is to break. So hopefully
it has like 120 sensors or something ridiculous like that.
Yeah. And that's because throughout the base area where the plants are growing out of is some dwarf wheat, they have sensors in all the different locations, so they can see when a dry patch is forming on the corner or that kind of thing. And so this has been used so far for one big Arabidopsis study, and we're waiting for that data. That'll be out next year or something like that. The advanced plant habitat's pretty cool. It's got a camera in the back. It's got a big LED light rack on top. It scrubs ethylene out of the air and other chemicals. And it can maintain gaseous composition. But because it's so advanced, it makes it really hard to use, and because it breaks. The veggie, on the other hand, has been shown to successfully grow lettuce and everything that we need. The biggest problem is watering the plants. And this is the new piece of hardware that's being tested right now on orbit.
So we have a call next week with, we already chatted with David Kasuma over at Tupperware.
So I won't go on about ponds anymore because you'll hear it from the horse's mouth, but fingers crossed. It looks like a really interesting tool, and I hope it works this time.
Yeah, well, third generation, I guess, or third test attempt. We'll see.
Yeah. So this is the coolest thing I've ever seen. And this is up on the space station right now. It went up.
I saw this at the last R&D conference.
So the spectrum analyzer. So right now on the space station, we've got some Petri dishes with some plants. This is some Arabidopsis seedlings on a carousel along with some yeast. And the plants are being photographed by their camera. So the camera is there in amongst these excitation, these lights. So they can illuminate the plants with green, blue, red, the major frequencies of light, and use that to excite fluorescent proteins. So fluorescent proteins are proteins from like jellyfish or fireflies that glow when you excite them. So for example, this one called green fluorescent protein glows green when you excite it with blue light. This one here called the red fluorescent protein glows red when you excite it with green light. So this is a really cool piece of kit, and you don't get sample return when you use this, so you just get the imaging back. So you have to attach these fluorescent proteins to promoter sequences or genes of interest. And so you can see by this little sticker, we're testing it right now. So we sent samples up, the images are coming down via telemetry, but we're not getting the samples back. So essentially we've created Schrödinger's plant. So we have a plant in a box that we can't open, far away, which has a radiation source. And people asked me the other day, are those plants dead or alive? Well, technically, according to Schrödinger, they're both dead and alive all at once, right? Anyway, it gets complicated. But the reason I wanted to bring this up was actually to show you this picture here. So earlier you were talking about some of the next generation spaceflight hardware. And that got me thinking of Orbitech and this guy, Bob Morrow. This is Rob, he's awesome. And he gets excited really easily, as you can see when he posed for the National Geographic photo on the article they're writing about the work they do. And you can see this growth system. They envisage in the future of space exploration purple walls like this with loads of plants growing. You can see the current design has 4 different chambers. Each of these chambers has an aeroponic system that's been tested in parabolic flights thanks to the Wisconsin Space Grant Consortium.
So this is you're talking about an aerosol then of water, basically?
Pretty much, yeah. And they've got some sophisticated method that then kind of wicks the aerosol once it sediments onto the surfaces and then like pulls it out. Because if not, eventually you'll just drown. They'll just drown. And we hope to have that on orbit one day. Well, he does at least, yeah. Here's a funny thing. So he grew potato in here because obviously that's where you want to go in space because of the movie The Martian and the book The Martian. So first of all, the potatoes are big plants. So what they did was they took all 4 chambers, they combined them into one and they grew a potato in there. Can you guess what happened? The potato filled the whole area, became really viney and really rooty and didn't produce any edible potatoes. Then what they did was they just divided it into the 4 chambers, the 4 sections that you can see, and they put potatoes in there. Somehow the potatoes grew, they knew the size of their environment, they were able to sense it perhaps mechanically, and they stopped their viney growth and instead put the extra energy into tubers. So thanks to the research of Bob Morrow and his team at Sierra Nevada Corp, we do have the knowledge and protocols that allow us to grow potatoes in orbit. And on that note, I'm going to have to leave because I have another telecon with some other folk. And thanks again for letting me join your conversation.
You are always welcome. I'll just keep a tab of the pints that I owe you.
You know my bill. Good.
I'll reach out to you and to keep our conversation on about what we can do to, whenever small way we can, aid in the research that you're doing at Gilroy Lab in Wisconsin. Really pleasure that you joined us today. Excited that you can take us on these journeys right there on the edge of discovery. Teachers, we hope that Dr. Nether can join us again in the future.
Oh, awesome. And I'd just like to say, I just shared the methods paper that shows people how to use a 2D climastat to detect gravity sensitivity. And the legend that is Paul Williams.
Yep.
He's the gentleman with the milk cart on the back of his bicycle.
Yep. So as you can see, everything is all recycled, handmade.
I love it.
This all stems from the foundations that he laid all those years ago. So you have to know where you've been to know where we're going. Yeah. And again, thanks for your time, and I really must depart. So
yes, thank you, Richard.
Thanks, man.
So we've got a comment question from Terrence Clark.
Yeah, I saw that.
He's a friend of mine.
A friend of.
He's a friend of mine. Yeah, he knows loads about aerospace. He's a big space nerd. He's great.
Okay.
Hi, Terrence.
Like, I can't wait to see the commercial modules fly. Referencing Bigelow. Bigelow's been so relatively quiet for so long. It was good to see Beam fly, but it really misses the big advantages of inflatables. So I think this comes back to some of the points you were making, Ted. Yeah, they really need to put one of the 330s up to prove out the advantages. Yeah, I mean, I'm wondering because if they could, how difficult it would be to create one that just remained in orbit for a period, and have it be sacrificial. But what kinds of experiments could you run during that orbital period? And if you boosted it high enough, you could probably get several weeks out of it.
Well, there you go. Well, the big thing, as I understand it, is just the cost, the up mass, right?
Yeah, that's always the hurdle, right?
Having these ribs with this this inflatable, you not just reduce the. Well, I guess the mass is fundamentally the same, but the volume, right, becomes something is also precious. So, and it's just expanding. You need obviously the oxygen and the nitrogen, whatever, to fill the thing up and pressurize it to 1 atmosphere of pressure. But yeah, man, what do we need to do that?
I mean, it wouldn't have to be that large of one for a plant study.
Right. Now, there's other opportunities as well. We've been talking about getting out on the porch or on things like Bartolomeo.
Right.
Where you have the extremes of space where you've got.
For those that don't know, the Kibo, the Japanese lab, has its own external laboratory. It has an airlock and its own robotic arm and so that area of Kibo is referred to as the porch.
Yep. That, or I guess Bartolomeo is another project through Airbus where you can, what they're doing there is, I guess, ultraviolet light studies on materials. Basically, you get a little chip of whatever you're looking at and you put it out there for 6 months, and you bring it back in and you kind of see whether or not your dashboard's going to, fade on you or crack or what have you. So that's kind of interesting, but looking at microbes and how those might be affected would be interesting as well. I don't know about our plants, probably wouldn't do very well out there in the direct hit with the direct light and the temperature changes swinging as much as they are. So with about 12 minutes left or so, Michael, why don't we do everyone a favor and kind of loop back through our whole program again. So Magnitude, our job really is to bring learning right to the very edge of discovery. We've been doing this for about 7 years. Our 7th mission is just now concluding. We were put in the flight bag to be sent home yesterday. We'll arrive back on Earth April 10th, I believe. And we're primarily looking at plant biology and bacterial investigations. But our lab itself is designed off the cube labs that are in space. This is the lab in the classroom, 2U equivalent. This is the lab that typically looks like when it goes into space. This is a 1U equivalent. Think about it like a 10-centimeter cube. Intermodal transportation for space. And so instead of a 40-foot container on the back of a truck, you got something like this can go to space. This is expensive, relatively speaking. It's inexpensive. Going to space can cost upwards of 6 figures or more, $100,000 or more. You can get more affordable, maybe 40 or 50,000. Our flights to space are only about $500 per school with the hardware. It's about 900. But because of the circumstance we're under right now, this pandemic around the planet, my team here at Magnitude opted to look at introducing something where there was no cost at all. It was all about using your creativity and your curiosity and your imagination to help us select our next candidate that we're going to fly. So we're not asking anyone to spend any money or to create any kind of special, unique system. If you have internet access during the stay-at-home period, by all means, log in. We have free accounts now. You can get the lesson plans and you can call and follow along at a little higher order. But we encourage you to just look at a really even more basic thing. We're trying to select a number of legumes or down select from a number of legumes to what we want to actually fly. So I guess what I need to do is probably log out of this real quick. And this is when your help comes in with you and your students. Anywhere from, honestly, from pre-K to 8, to pre-K to university. Let's find a way to engage your students through think about it as a design challenge, a creation of an argument for why a particular plant may be a benefit for us to fly. We have a relationship that we're exploring right now, a symbiotic relationship between a bacterium. This is Rhizobia, which has a really unique relationship with legumes. They've got a little barter system going on where the plant exchanges carbon in order to get some nitrogen, which the Rhizobia generates a copious amount, enough for itself and for the plant host. And this is really where green fertilizer and the whole idea of using legumes as an inner a part of your crop rotation where it becomes of value. And I'll share this with you, and I'm going to turn to Michael. Why don't you share a little bit more about this while I should share the page?
Sure. So we've got several legumes that we're putting out there, proposing. The one in front of me is a cowpea, also called black eye peas. And this is one that started out in the test tube in the exolab, but then because it was doing so well, pulled it out, and it's been living a couple more weeks out of the lab, and it's actually flowering and producing pods now. It's got looks like one flower to open later today probably, and it's got 1, 2, 3 pods so far. And later today we're actually going to do some dissection work with this one. We'll take it out and take a closer look at the relationship between the Rhizobia, the bacteria that's in the soil, and the legume and its root system. So any reason for putting these plants on orbit is a valid one, and there's a lesson plan that you can consider as a way to launch all of this. So I'll give you an example. So I'm heading up Team Clover, and the reason that I thought of Clover was just fond memories of a kid growing up and nibbling on the clover blossoms. You know, just, they're sweet, and it was, you know, just fun. You can throw them in as a sprout to add some flavor into your, you know, your salad or whatever. It's good nutrient values. And you know, I'm also thinking about the size of the plant. Maybe we can do better. So there's all kinds of reasons, both just personal, emotional. You know, thinking if I were on orbit and I were able to nibble on these clover blossoms the way I did when I was a kid, you know, staring up at the sky and thinking about being out on their orbit, it would really connect me emotionally to myself and Earth and just, you know, everything. But then just thinking about the biology of it all, what we can learn from it, there's all of those aspects. And as Ted said, it can be any age. It could be a young child who's just thinking, I like this plant. I see it in my backyard, or grandma makes a really good chickpea recipe that I'd like to be able to make in space. And, you know, whatever the reason is, a crayon drawing, a technical white paper that an older, more sophisticated student might do, and actually create a little bit of research in there, if they'd like to. We've got, within our teams, we've got the seeds. We're actually going to be starting to grow these, see what they look like, and evaluate them for their growth characteristics. But we really need your excitement and interest, and that of your students, to really push this, because it's got to be appealing to us as people. We're not robots. We've got to have real reasons for doing these things.
Mm-hmm. Wow. So we have some new folks that have joined us, and it looks like we're starting to get some folks from around the world. And these sessions will be running for the next 34 days. We launched yesterday, first day of spring. We're going to run through April 22nd. Michael Wilkinson here is our lead educator, working with a team of teachers. Each one of them is kind of representing some of our plans candidates here, help us determine what we would like to fly. And so we've got Man Elementary that has joined us. Welcome aboard. If you got some questions, anyone has some questions, please reach out to us. I'll give just team at Magnitude.io reaches all of us, and we can address it as needed, whether it's a technical, engineering, biological, a pedagogical, whatever question you might have. We're here to help you out. We're really just one community here, trying to make the best of a quite unusual circumstance that the world's going through. We have Akdeniz University in Turkey. So welcome, Turkey. Thank you for joining us at the university level. I'm really excited and encouraged by the work that you might be doing, or how your students might be engaged. So let's talk about that. The Foundation Academy. So welcome. I'm not quite sure where you're from. And Campbell County Middle School. Hello, and welcome to us in this global challenge to help us find on this next mission, Mission 8, Exolab 8. It's going to be flying in August aboard SpaceX 21. It's a 2U equivalent lab. While we have that running in orbit, we typically have these labs running across classrooms around the world. It's not a mandatory for anyone to buy any equipment for this design challenge. It's open, it's free, it's about community. We want you to help us determine what the best candidate would be in this amazing relationship between this bacterium, Rhizobia, and a legume. Which one? And there's some legumes that aren't on this list. So if you're passionate about peanuts, it's not a nut, it's actually a legume. Maybe we want to add a peanut in there. So help us understand what you love and get behind a team. These teams will be kind of formed ad hoc. If you really love Adzuki, go Adzuki, or alfalfa. You can start creating for your younger kids, as Michael mentioned, maybe it's art or poetry. Throw something on TikTok, give us a hashtag. Or it might be something with your high school biology students, honors or AP, something you want them to work on, or something they're very excited about. Have them do some research. We were really fortunate to have back-to-back days with Dr. Richard Barker from the Gilroy Lab, a Wisconsin laboratory there that does the most extraordinary work in microgravity with plants, with a primary focus on Arabidopsis. Now, Arabidopsis is a model organism, kind of like part of the mustard family. Its genome has been fully mapped, so it's usually a great plant to begin your biological research in, whatever you're doing. In this case, we're looking at taking out that force of nature, gravity, and we're taking it out of the equation for the most part. And oh my goodness, what happens? There's a lot of crazy things happen. Can we build sustainable crops beyond Earth? Can we think about how plants might behave in this unique environment that suddenly helps us understand more about how we can make them do better here on Earth? Maybe more drought tolerant, maybe able to grow in brackish water, maybe able to produce more for our growing population on Earth. So
yeah,
this
salt
is
tolerance. Sorry to interrupt you, but the salt tolerance is really, we learned yesterday from Richard that that's a huge issue, because the regolith on Mars has a very high salt content because of the evaporation of the water.
That's right. And if we look around the world, this potable water is very small, very, very small percentage. And outside of doing some things like capturing moisture from the atmosphere directly, there are we're going to be in some pretty serious issues. Your desalinization plants, what have you, they get crusty after a while. They're getting all those salts and your filters get filled up. You got to replace those. It's not a perfect solution. There's some organic things people are talking about, but can we get plants to behave in a manner where we can feed the population? If we've got farm animals, where I think as a society, it looks like we want to move away from that, but we still have that. We have to be concerned about it. What can we do to kind of help plants help us and this relationship with all the other living things on our Earth? So we hope, if anything, we're just opening up a little excitement for your students, for you as teachers, or if your students watching us, if your parents trying to find something for your students to do, reach out to us, team.magnitude.io. We're going to run this again today, 2 o'clock, little different theme. Michael's going to go through a dissection with a more mature plant here, about 5 weeks old. And we're going to look for those little nodules that are developed between the symbiotic relationship. We're going to talk a little bit about the anatomy. Get about about how you can kind of do your own simple experiment at home with, go out and find, if you've got a water bottle, plastic water bottle, get one of those and make it available. You might want a pair of scissors or a knife. Younger kids, obviously parents, you want to be by there to help them out. Teachers, maybe you're just building a lesson plan. Let's help you walk through that lesson plan. Magnitude.io will get you to a page where you can read more about what we're doing. There's an easy sign up. If you have that and you want to go down that route, you can. I don't know if we have our PDFs available yet. We've been doing all this literally on the fly since last week, knowing that schools are shutting down. All of California shut down. Where we are, we're based in Berkeley, California. I know across the country in the United States, it's happening around the world, right? And so we want to be strong and kind of stay true on our excitement and interest, and not be too swayed by those things we can't control. We wash our hands, keep our social distance, as they say. But we're not really socially distant, are we, Michael? You might be in New York and I'm here in California, but we're pretty close right now, thanks to the digital world. And so come join us, whether you're from Turkey or from other parts of the world. We're really excited. Share this with your friends, share this with your colleagues. We'll see you back again at 2 o'clock. And over the next 34 days, I don't know what the calendar is going to look like, but if you have an idea, team@magnitude.io, send it to us and come on to this side of the screen and share your background with us, and perhaps a new way to share your teaching with kindergartners, 5th graders, 8th graders, high school students, university students. We're really excited that you are listening in and join us for this program. So thanks again. I think what we'll do is we'll wrap up for today, and we'll catch up with you at 2 o'clock Pacific, 5 o'clock Eastern. UTC, I guess that's 8. So what is that? Midnight? No, 10 o'clock? Something.
22. Yep.
Yeah, 10 o'clock. 10. I know that's kind of late. So we do have schools in Africa and schools in Europe and Germany. We're going to set some of these up next week where they're a little more accommodating to your schedules. If you did join us from like Turkey, wow. But let's find a time that's a little more conducive to that GMT plus or minus an hour or two. So look for those coming next week as well. Michael, thank you for joining me for most of this day. Dr. Barker, I know you've already taken off for the rest of your day. Thanks so much for jumping back in again. We really appreciate your passion and insight, knowledge and expertise as we figure out what the heck we're doing. And until 2 o'clock or until next week, thanks for dropping in, and check out magnitude.io. And one final thing, we couldn't do any of this without Space Tango, our flight provider out of Kentucky, and the National Laboratory. The U.S. National Lab does research really for the betterment of life on Earth. Even though we're exploring these extraordinary things beyond the planet, we want to look back at the beautiful blue ball that we all live on, our one spaceship. We're all in it together. And if anything, this pandemic that we're kind of forced to shelter in place in, is a reawakening of us understanding that we all are connected. And if
Yeah,
we're
you
not
can see
taking
Liam's
care-
thumbnail there. That is us.
Yep.
That is us live.
Yep. And thank you, Liam at ISS Above, for allowing me to have this in the background and having that live stream of Earth from the space station. So catch back with us again at 2:00. Keep that conversation going. We'd love to hear your ideas. Pick a team. We need some support for these different teams. I'm Team Atsuki, just so you know. All right, good deal. We're going to sign off for now. We'll catch you a little later today. Michael,
right,
thank you. And Liam, thanks for hanging out with us. Come join us a little later too, if you can. Take care, everyone, and we'll see you soon.
Be well.
Bye now.